Hello my dear students, I welcome you back to the Chemistry One-Shot series at our PW JEE English channel. Today we are continuing our discussion on physical chemistry and building up that confidence with the new chapter of thermodynamics and thermochemistry. Some students fear this chapter, but you do not be scared because I have personally made this chapter very concise that this video will be more than sufficient for you to make the right question attempt at your JEE examination. Do not worry because you will be definitely landing up with one question, but maybe two. The lecture notes and the related DPPs for this lecture, you can download it for free from our PW app, the link to which is given in the description box. PW is one of the largest educational organizations trusted by millions of students every year preparing for their competitive journey, both in the field of JEE, NEET, and many other competitive examinations. So let us dive deep and explore this side of physical chemistry. So basically, thermodynamics deal with the study of heat exchange between system and surrounding. System is that part of universe which you will consider under your study, which will definitely exchange heat with the surrounding. So sir, what types of system we have? Basically, we have three types of system. Discussing about the first type, which is an open system. Although it's a basic, but I'm dealing with all the basics, so do not worry. What are open system? Like a cup of tea. A cup of tea can exchange heat also with the surrounding. It can exchange, you can take a sip or put on some extra tea in it, so it can exchange matter also. The boundary by which this system is separated from the surrounding, you can see this cup body is a real boundary. If I can think of an imagination of a lid with which, if it is covered, will separate this system from the surrounding, will be an imaginary boundary. So these boundaries are basically diathermic in nature, as in they can allow the system, the matter present in the system, to exchange heat with the surrounding. So what's a closed system, sir? A closed system is when that imaginary lid you have exactly put on. Now you cannot take a sip or pour tea inside it. So this system will not exchange matter. Obviously, it will only exchange heat with the surrounding. And the third type of system is an isolated system, which will exchange nothing because it is closed also, and the boundary is adiabatic. So what's an adiabatic boundary? Which will not allow the exchange of heat also between the matter present in the system and the surrounding. A basic example of adiabatic or a adiabatic boundary having an isolated system is a thermos that you must have seen in your home. Now, practically speaking, if you keep a thermos full of hot milk, will the milk be hot the next day also? So practically we know there is no system which is a perfect isolated system. So if someone snatches your neck and asks you, can't you give me even one example of a perfect isolated system? We have one example, which is the universe, because universe is everything. So that everything will exchange heat from what? So actually universe theoretically is an example of an isolated system, or else a perfect isolated system is not possible to be built by us or by nature, as a matter of fact, because that system will definitely exchange some heat with the surrounding. Now what people ask is, sir, if I put this tea in this room, definitely I know heat will exchange from the tea to the surrounding. Why not opposite thing takes place? That all basics will be dealt by the second law of thermodynamics, and the amount of heat that is allowed to flow from the system to the surrounding, we'll deal it with the first law of thermodynamics. Sir, why you are telling us this basic? Move directly ahead to those topic, because with the same basic theory, a question was framed in 2023. Have a look over the question. So if you just see through this question, I guess you must have attempted it, that it is saying system A is adiabatic. Okay, sir. So what does an adiabatic system do? Will not allow energy to be exchanged. So if combustion is taking place in a box, heat will be released. If heat will be released, temperature will rise. So what options are asking you? Temperature will definitely rise for system A. Option A is saying it will rise, yes. Fall, no. Fall, no. Remain same, no. So I guess with first option, with system A only, you got your answer. So just check option B. What diathermic system, sir, we know that is a system which will allow the exchange of energy. So if combustion is taking place, heat produced will flow out. If flows out, then temperature will remain the same. So temperature remains constant. This is a basic that theory is asked in JEE. Moving ahead. Now, what are extensive and intensive? As student, I always used to forget it. So I made a keyword. Intensive. I have remembered it with the word independent. So with intensive, we will say, or we will always speak independent. So independent of what? Independent of amount of system. Whatever matter present in the system, if I am a property and I have no effect of the amount present in that system, so I will be an intensive property. And what will be extensive? If I will depend upon the amount. Depends on the amount. Sir, okay, it is easy for theory, but sir, please explain. So let me explain. Let's say I have this bucket of Rasna, cold drink. You just divide this bucket of Rasna into half. So it is whatever property got halved, they are depending on the amount. So depending amount, so they are extensive. And if they are same, so it is intensive. So what can you say about volume? Sir, if it is 1 liter, you have halved it, it will be half liter. Definitely right. So volume will be what? Sir, volume will be intensive or extensive, sir, depending upon amount. So volume will be, so your volume will be extensive, depends. Sir, mass, if I've taken this mass is, let's say, 1 kg, if divided into 2, so mass is also extensive. Now, sir, what about density? Density is, sir, density as in the thickness. If let's say I put a spoon in this half, sir, it will be same liquid. This also will have the same almost density. So I am giving you a common sense as well. What is density, my friends? Sir, density is mass per unit volume. So whatever quantity which do not depend, density remains the same. And there's a statistical observational fact about this. Ratio of two extensive property is always intensive. I'm just talking about the mathematical operation of division, not multiplication, not addition, not subtraction. Ratio, if you divide two extensive property, the resultant will always be intensive. Moreover, sir, if extensive property is depending upon the amount, so if we add it, it will be added, yes. If we'll subtract it, it will get subtracted, yes. Sir, throw some okay, some examples first. Before that property, some examples first. So first, some intensive properties. All concentration terms, whatever you have studied in mole concept in solution chapter, molarity, small m is molality, parts per million, formality is molarity only, but for an ionic compound, instead of molar mass, we term as formula mass. So molarity becomes formality. Normality, percentage, whatever strength, whatever concentration terms you know, because they are always ratios of extensive property. So they are always intensive. This is point number one. Point number two. This is point number one. Point number two, all temperatures, all melting point, boiling point, freezing point, whatever temperatures you have, they do not depend upon the amount. Let's say if let's say it's a rasna you have just taken out from a freezer. So if you divide that glass, I have given half, I am drinking, half I have given to my brother. So will the temperature of that cold drink, that rasna, change? No, sir. So temperature is also, all type of temperature are also intensive. Specific. Now, whenever in this chapter we'll see specific word, whenever specific charge or specific mass or specific heat capacity, whatever these terms we will be discussing in this chapter. Specific means my property with respect to my weight. So what is specific heat? Heat given to a system per gram. So because per gram, so ratio will make it intensive. Similarly, any property per mole taken, those are called molar properties. So molar properties are also always intensive just because of the fact that extensive upon extensive makes it intensive. All equilibrium constants, Kc, Kp, they are always intensive. Moving forward, sir, what about extensive properties? Whatever thermodynamic properties, sir, thermodynamic is study of heat. So heat and the corresponding energies, they are always extensive. Like internal energy represented as capital U, enthalpy, capital H, entropy, capital S, Gibbs free energy, capital G, so all possible types of energies will depend upon the amount. And in order to make them intensive, that's why in questions what value are given for these properties? Per mole. So per molar value of these energy will again be intensive. But these properties as a whole, as a unit, as individual, these energies are extensive. Molar value of them will become intensive. That's why we use molar properties. Now, just to discuss about their additive nature, I am using this slide which I was yes. Just to show you that they are additive. So let us take an example for that. For example, let's say this stub, we can clearly see, sir, it is half, it is double. But I'm just trying to show you they are additive. Let's say its mass is 10 grams. So what will be the mass of that bucket, sir? If this is 10 gram, let's say this is 20 grams. So you tell me, if you add them, if you mix them together in a bigger bucket, I'm representing that bigger bucket over here. So what can you say about the total? So 10, 20 will become 30. So mass is an extensive property. If you add, it gets added. Let's say, for example, its moles are, let's say its molar mass is 2, for example. Its molar mass is 2. So its molar mass is also 2. So if both are added over here, its molar mass will also be 2. So molar mass per mole. So molar mass is extensive. So leaving that. So let's say 2 is its molar mass. So it will be 10 by 2 as in 5. What will be moles over here? So 20 by 2 as in 10. So what moles I am adding over there? 10 plus 5 is 15. Will it has 15? Let us check. How you will calculate moles of this total mixture? So total moles will be equal to total weight upon molar mass will remain the same. What will be total weight? Total weight is 30. So is 30 by 2 equal to 15? Yes, sir. So extensive properties are additive in nature. Similarly, volume you can definitely, let's say this is 1 liter, so this is 2 liters, so total will definitely be 3 liter. Yes, sir, additive. Now, density, sir, density is ratio, mass by volume. So density is intensive and therefore intensive property never gets added. Intensive property never gets added. Let's see. What is density of this solution, sir? Mass of this solution is 10, volume. Okay, I am calculating density in gram per liter. My wish. So this density is 10 gram per liter. What about this? What about this? Sir, it has a mass of 20, volume of 2. So this is 20. This is also 10 gram per liter, its density. If you will mix it, sir, its density will also be 10 gram per liter. Just check what is the total mass. Total mass is 30. What is total volume? 3. 30 by 3 is also 10. So intensive properties are never additive. Similarly, you can say for molarity also, because here you have to calculate for total, you have to calculate total moles. So total moles will be moles of this is 5 and this is 10. Total moles is 15. So molarity is 15 upon total volume is 3. So volume molarity will be 5 molar of the solution, of the total solution. But molarity of this solution will be 5 by 1. So this will be 5 molar. Molarity of this is 10 by 2. It is also 5 molar. So molarity of the resulting solution is also 5. So because molarity is intensive, so it is not getting added up and remaining the same. So this is what students get confused a lot. That's why I've given you example. So just a final word: extensive upon extensive becomes intensive. First, extensive properties are always additive while intensive are not. So these are some basic theory, which obviously questions are also questions. Why I'm discussing this? Because there will be questions. So this question says total number of intensive properties. Sir, we have recently done that. So let's mark. So intensive is independent. Sir, volume, no. Molar, heat, molar, anything per mole taken is intensive. Molarity, sir, ratio, intensive. E naught cell, you will see in electrochemistry, E naught cell is actually potential. The word itself signifies. What is potential, sir? Potential is the basic definition through also you can say. What is potential, sir? Work done to move a charge. So ratio of extensive upon extensive. Work done with complete system, with half system, half will be done. Complete system will having 10 coulomb charge, half will have half coulomb charge. So extensive upon extensive will become intensive. Next is molar mass. This molar mass is also intensive. So how many pink we have? 4, I guess. So let's just take the other one. Volume, sir, extensive. Gibbs free energy, any energy is extensive. Mole, extensive. So here's the answer. You get such theoretical questions, so deal with it. Moving ahead. Now, state functions and path functions. Reason. Remember it. If a system is moving, let's say from point A and reaching till point B, the basic, I'm through physics also you can see. So if a system is moving from point A to point B, now all those properties who depends on how I'm going from point A to point B are called path function. That is, depends on how A to B is reached. Then you are dependent on the path by which your state has been changed from state A to state B. Then you are a path function. And if you are independent of that, then you are a state function. So it is independent of path. Independent. Okay. So, for example, I'm giving a basic distance and displacement. Let's say this A and B are 10 meters apart. So displacement is 10. Displacement is a state function. I have no problem how you have came from point A to point B. But so this is displacement. So displacement is a state function. While distance, sir, if I'm reaching like this, I can either take this route, I can either take this route. So distance will depend on the path taken for reaching from A point to B point. So you kindly just look at the options and try to give an easy answer. Yes. So moving forward, let us now list some more examples of state and path functions. As we have already discussed, these state functions which has nothing to do with the path followed by a system when it has reached from point A to point B. Some more examples are all the thermodynamic variables that we will be seeing, that is pressure, temperature, volume, and thermodynamics variable like internal energy, enthalpy, entropy, Gibbs free energy change. We are just going to discuss about these variables, but whatever properties of a gas like its pressure, volume, temperature, and all these thermodynamic factors, they all depends on the state of the system and not on the path by which the state has been achieved. One more very important thing, because in order to calculate the absolute value of the system, like for example, if I need to measure that what is your IQ, so exactly quantifying the exact value. For example, another example, how much is your eating capacity? So instead of, because someday you can eat a lot, someday you cannot eat that much. So many a time, practically, it is very difficult, close to impossible, to calculate the absolute value of any system at one point of time. So instead, what we can do really easy is to find a change. For example, there are two boys, boy A and boy B. If I need to check who has more eating capacity, I can observe a change. I can offer them to eat for like 10 minutes, and the boy who has eaten more will be, the change will definitely show the eating capacity of the boy. Similarly, of a system, if you need to calculate the absolute value of the system, rather, it is quite easy to calculate the change from point A to point B. So practically, change is very important for us, and that's why discussing these state functions and path functions and focusing on the state functions. Now, as we know, mathematically, when you draw a graph for a gas, you have to know its value at each point of x. You need to know the value of y, then only that graph will be continuous. So what is small change for us mathematically? Sir, dx, differentiation, or delta x. So similarly, small changes can also be observed, and the small changes we refer as du, dh, or ds. Sometimes you may also see like delta u, delta s. So these all represent small change which very well help us while doing mathematics. We will definitely see later. Now, if the change is large enough, how do you represent a large change? By a delta sign, that is final minus initial. So this is how you can represent a large change for state functions. The path functions that you basically mostly be seeing in your chapter of thermodynamics are basically three. Work is a path function, heat is a path function, and another type of heat, which is heat capacity. We will be defining it in the later slides. So these heat capacities, they are specific values for per mole, per gram. So these heat capacities, they are also path function. And mind you, we in chemistry, in physics, you may do that, but in chemistry there is nothing called delta W or delta Q. Why? Because if you have started from state 1, how much work has you done? Sir, we have just started, so how much work we have done? 0. After reaching point 2, from initial state to final state, after reaching point 2, the final state, how much work you had done? W. How much heat you have given? dq. Yes, the small heat given may be termed as dq. The small amount of work done may be represented mathematically as dw, but we will never define delta w and delta q for our path functions, is what you definitely have to keep in your mind. That's why I have lasered it and not written it, so that it may get removed, that mathematically you can do. Mathematically, we'll see how we can use them. Moving ahead now. Next is the types of system. Sir, what are types of system? These are basic theory. I'm just rushing through it. So we all know we are defining all these when all these processes generally, when the system generally given to us contains an ideal gas, because real gas and ideal gas, the kinetic theory of gases, the whole states of matter, the gaseous state chapter from class 11th is removed from board syllabus, also is removed from JEE mains syllabus, also it is there in advanced syllabus. So we have already discussed the PV equal to nRT and some relationship in the mole concept. Those of you who haven't seen it, kindly refer mole concept. But we are definitely generally speaking of ideal gases, and ideal gas equation is PV is equal to nRT. So we'll have to keep that thing in mind. So what isothermal process? So by name suggests, whenever a process, a gas or any matter, as a matter of fact, if it is reaching from state A to state B, And during the transfer from state A to state B, if overall the temperature of the system is maintained to be constant, such a process is known as isothermal process. Isothermal process has T constant. So if T is constant, its change, that is delta T or even dt, the small change, it will also be zero because it's an isothermal process. Now, this is a very important point. Phase transformations. Whenever a solid changes into liquid, a liquid changes into gas, that is the boiling and melting point, the temperature never changes. The let's say H2O liquid freezes at 0 degrees Celsius until all the liquid has been solidified into H2O solid. The temperature will not change. Similarly, if liquid is boiling, H2O liquid, until unless whole of the complete of the H2O liquid is converted to H2O gas, the temperature will never change. These things we all know. I'm just writing one more example for you. Like H2O liquid changes to H2O gas. So until and unless whole of the liquid changes to gas, the temperature remains constant, and it is called, we very well know, it is called boiling point. Similarly, when solid goes into liquid, freezing point or melting point, whenever phase transformation takes place, temperature is always kept constant. That is, phase transformations are always isothermal in nature. When you draw the graph, the PV graph for an isothermal process, obviously, because from ideal gas equation, you know PV is equal to nRT. So for a specific amount of gas, obviously, I'm assuming amount of gas to be fixed, because if the system that is under our observation for the heat transfer study, the system will definitely have some fixed moles of gas. So for fixed moles of gas and constant temperature, PV equals nRT. If N is constant and T is constant, R is always the universal gas constant. That means PV will give you a rectangular hyperbola, as in this graph will be termed as isotherm. The next process is isobaric, pressure constant, delta P 0. The curves are called isobars. So a PV graph will have constant pressure. You keep on increasing volume. A VT graph will be a straight line, because in PV equal to nRT, if P is constant, N is definitely constant. So V is proportional to T. So it's a straight line. Why I have not passed it through origin? Because 0 Kelvin can never be attained. So practically, that's a correct graph. Next one is isochoric process. Curves are called isochores. So this is an isochore with pressure. This is an isochore, a straight line passing through origin, because if V is constant, then P gets proportional to T. Moving to the next process, the very important process, adiabatic process. As we have already discussed, during adiabatic process, what type of boundary you have? An isolated boundary. Between system and surrounding, nothing exchanges. That is, heat exchange is 0. There is no delta Q for us. So Q is 0 because heat exchange is 0. Let us say I have a gas in the system and a pile of sand, more amount of sand is placed onto the top. Let's say gas is there in the chamber with volume V1, temperature T1. If you by any means, if you remove the sand from the outside, what you observe is less amount of sand. Gas will suddenly feel weight has lifted from us, it will expand. But if they are working, if you are not given any food and still you are asked to work, you will be working at the cost of your internal energy. That means you will get tired. Similarly, if gas, because I'm saying the process is adiabatic, so there is no heat exchange. So my dear friends, if there is no heat exchange, and if a gas expands from volume V1 to V2, because we can clearly see over here, this V2 volume and this V1 volume, we can clearly see V1, V2 is much greater. So it's an expansion. Sir, if gas expands, it has to work. Yes, it definitely has to push the piston. And in order to push the piston, temperature will definitely fall, because it is not getting any supply of heat from outside. So obviously over here I can say T2 is much lesser than T1, because gas has gas has cooled down. Why? Because it has done some work, sir. And if you'll work and you will not get any energy from outside, you will be working at the cost of your own internal energy, and your pressure and your corresponding temperature will get decreased. You will get tired. Gases, the kinetic energy will definitely get reduced. Moving ahead. Cyclic process. Cyclic process, by the name suggests, let's say I have a system, a gas going from state A to B, then to C, then to D, and coming back to A. So it's a cyclic process, and during a cyclic process, I started from a point, I ended in the same point, so all the state variables will be 0. Now, just to put a frame into it, all you guys, just help me with the data filling. Can you comment on the types of process AB, BC, CD and DA? Yes, so now I'm quite confident you must have seen that from A to B, since pressure is constant, so first word is the process is definitely an isobaric process. Now, this over this temperature is constant, sir. Isothermal, but isothermal was a curve, sir. It was a curve for a PV graph. It's a pressure temperature graph. Mind you, please, my dear friends, whenever graphs are given, at least first check what the graph is present. So, A to B is isobaric, but isobaric what, sir? It's a gas, an ideal gas. Pressure is constant. Therefore, volume must be there and it will be proportional to temperature, because A to B pressure is constant. Moles are definitely, because system is fixed, or moles are constant inside that box system. Now, volume since is proportional to T, so if you see from A to B, temperature is increasing, so definitely volume will also increase. So we'll say it's a isobaric expansion. Moving ahead. Now, can you comment about B2C? Sir, definitely I can see temperature is constant. So, do PV equal to nRT? So, PV will become constant because temperature is constant. Now, you tell me, since pressure is decreasing, so in order to make PV constant, volume should, pressure is decreasing from B to C, so volume should increase. So, it's isothermal definitely because temperature is constant, but because pressure is decreasing, so P decreasing should increase V. So, this is isothermal expansion. I hope you're getting this. Now, from C to D, it is just opposite, because C to D, pressure is constant, but opposite of AB. So, this is again isobaric, but opposite, as in compression. Now, these things you have to watch via some mathematical observations. And again, D to A will be, obviously temperature is constant, so it's a isothermal process. But isothermal what? Again, a compression. I hope we are making sense over here. Moving ahead. Now, okay, and let's start discussing about the thermodynamic variables. Sir, what are these variables? How are you supposed to define the state of a thermodynamic system? How are you supposed to study the heat flow into or out of the thermodynamic system? So, any system, if heat exchanges has to be studied, I need some variables. So, let us define those variables. The first variable is internal energy. We very well know whatever type of energy, we already discussed, whatever type of energy I have, the summation of all those possible energies which a system possesses is known as its internal energy. Sir, it is definitely very difficult to find the absolute value, as we said. So we will find the change. And finding the change is practically very easy. Why? Because what cases generally do we get, sir? Gases. So if you have gases, because states of matter is out of our syllabus, so I am giving you one solid conclusion. Actually, internal energy of the system, the very first point, internal energy of the system we are representing as U. NCERT also refer it as capital E, but generally you find U. So you should know U and E both, but I'm using U. So U is basically sum of all possible kinetic energy present in the system. Sir, but present in the system. Present in the system, obviously. So, sir, but there are various other energies. But what do you find? Delta U, the change in internal energy, or maybe du. So du is also a change, although small change, an infinitesimal change. So whatever case may be, you are definitely interested in the change, and when you find the difference, the contributing energy that contributes to the internal energy is statistically seen as always the kinetic energy. And kinetic energy for 1 mole of gas, this I am giving you as a conclusion of states of matter. So kinetic energy, average kinetic energy of 1 mole of any gas. This is a conclusion of kinetic theory of gas. The value equals 3 by 2 RT. So the average kinetic energy possessed by 1 mole of any gaseous molecule is 3 by 2 RT. Obviously, we can see it is depending upon the Kelvin temperature. So you have to keep this formula in mind, very important formula, a direct conclusion of kinetic theory of gas, not deriving. In physics, you must be deriving it, but for as of now, you should remember this. The average kinetic energy for 1 molecule of any gaseous molecule is 3 by 2 RT, 3 by 2 RT for 1 mole of any gaseous molecule. So, sir, if it is so, then we know difference, therefore, delta U will definitely be equal to, okay, first of all, I am defining the U because, sir, you are saying only kinetic energy is contributing. So I can say the internal energy, although practically difficult to determine, but theoretically I am saying that this U is equal to sum of all possible kinetic energies, which is equal to 3 by 2 RT for 1 mole of any gas. Therefore, this U can also be equal to 3 by 2 nRT, but this is for n moles of any ideal gas. Moving ahead, some other characteristics this we have seen. Like all thermodynamic properties, U and delta U is a state function. State function as in it only depends upon the initial and final state of the system. Next thing, it is a state and a extensive or intensive. It depends upon the amount. So it is an extensive property. Already done, just writing. Now, one thing I'm asking you to keep always in mind that U is actually a function of temperature. Although, even if you miss this formula, you should understand this, that internal energy of any system is a function of temperature. So for isothermal process, if a gas is undergoing an isothermal process, sir, temperature will be constant. So if temperature is constant, delta T will be 0. So therefore, for isothermal process, you will definitely find for an ideal gas, its internal energy change will also be equals to 0. Sir, now, how can you change this internal energy? This internal energy of the system can be either altered, increase or decrease by two thermodynamic variables, two more thermodynamic variables, very, very important, and that designs your first law. So moving forward to the float of thermodynamics, that is first law of thermodynamics, which basically says is nothing but energy conservation. In physics, you will be dealing with float a lot, but in chemistry, thermochemistry part is more important. So I'm just finishing off with all this properly, but quite quickly. Now, so this is energy conservation. What is energy conservation? Suppose I'm a system, this is my initial state. I will have definitely some energy. Whatever summation of energy I'll have, let us say I'm having an energy of U1. So U1 is my energy at initial state. Now, how can you change my internal energy? The internal energy can be changed primarily by two factors, by heat and by work. The other thermodynamic variables, as we already seen, both are path functions. Now, it will depend upon how heat is given and how work is done. But let's say I am applying Q amount of heat to the system. I am giving Q amount of heat to the system. I'm also adding W amount of work on the system. Obviously, if I'm doing these two inputs, internal energy of the system will increase. Let's say finally it reached a state, and at state final, its internal energy has become U2. Sir, energy cannot be created nor can be destroyed. This is first law. Yes. Apply whatever maths, what maths you will apply. So you will say by energy conservation, U2 is equal to U1 plus Q plus W, simple. Or you can say delta U is equal to Q plus W. How delta U, sir? Beta, U2 minus U1. What is change? Final minus initial. So delta U is nothing but U2 minus U1. In absolute value, I am not interested, but I am very much interested in the change. Now, this is first law of thermodynamics, the mathematical justification, point number one. Very important. There's an observational truth also behind around it. Sir, delta U, the LHS is a state function, while the RHS is a path function. Keep this thing in mind. It is statistically coming out to be like this. So what can you say? This change in state function is coming out to be equal to path function. Now, point number two. Now, the basic difference of thermodynamics between physics and chemistry is physics is interested in the system. We are interested on ourselves. You know it from class 10th also. Whenever a system is exothermic, that is, system is giving you heat, you take that as negative value. And whenever you supply heat to the system, you take as positive value. So you just have to keep this thing in mind. Let's say you have a test tube. What do you want? Test tube should be exothermic and give splashes of heat on your face? No. You are important over chemistry. So when we don't want system to work on us, I will work on you. So do this sign convention for both heat and work. And remember this very religiously. Suppose someone is saying you, I am supplying 10 joule of heat to the system. So value for us is plus 10. Someone is saying I am doing 20 joule of work on the system. So my value is plus 20. Mathematically, I am writing it over here that heat given or work done where on the system is positive for us, and similarly the opposite thing, heat given by the system or work done by the system is definitely negative for us. So heat given or work done by the system is negative for us. So we do not want system to work. We do not want system to give heat. If it is doing so, the value you will be taking with a negative sign. We'll see many questions on that. This is your first law of thermodynamics. But sir, work? You haven't quantified anything regarding work. Let us do so. From how? From your basics of class 10th and basics of class 10th. But before that, let us understand the processes. The reverser, we have studied the process. I have intentionally kept two processes with me, reversible and irreversible. Now let us first go into this slide, this diagram. Let's say I am not interested now even if it can be isolated system or it can be any type of system. So this is any system. Any system. It can be isothermal, it can be adiabatic. I am not bothering on that because I am calculating my mathematical work approach over here. Now how? You tell me, let's say this is my initial state, for example, and I have poured a heap, a long pile of sand. Now I can remove this sand by two ways. I can directly remove it. For example, if instead of sand, you just think of an image that there is a latch, the one at the door, there is a latch. The pressure of the gas is more and I have stopped the gas using a latch. If I pull out the latch in a ziffy, in a click, the system will reach from here to here. Why reaching here? Because maybe at this point of time, the initial pressure, the pressure of gas and the external pressure would be becoming equal. Obviously, the gas will stop over there. So such a process which happens in a jiffy is called an irreversible process, because in an irreversible process, the equilibrium exists at initial and final state only, which happens in a single step in a finite time. And actually such processes are practical in nature. In physics, in practical life, we only do such processes. You know what's an reversible process? Have you seen sand, those microscopic small particles? Not microscopic, but very, very, very small. I mean, they will even get inside the gap between your nails and the fingers. While eating also they come when you eat. So those small particles of sand, if you start removing those small particles of sand one by one, obviously a time will come when that sand particle from this much will become only this much. And obviously, because sand particles are removing, so external pressure is also getting decreased. But it is getting decreased by infinitesimally small value. Can you tell me how much time you will take to remove one bit? You cannot remove more than one bit. Sir, we cannot do this process so slow. We are so, no, even though we are so free, but still this job will be impossible and a boring job for us. So how much time you will take to remove this much of sand and reach to this little amount of sand? Sir, I will be taking infinite time, but at that point of time, equilibrium will be at every step. If you have removed one particle, at that point of time also the pressure of the external pressure and the pressure of the gas will be equal. So what you have to just keep in your mind that reversible processes are theoretically validated. Why? Because you will be knowing the values of the system at each and every point. Suppose you are making a graph. So in order to make a continuous graph, you need points. For every x, you need y. But practically, you get those values of x and y at initial state and final state. So practically, the work you do is a irreversible work. And theoretically, ideally, ideal gas do not exist. So ideal work also is not literally experienced in nature. But if at all it is experienced, then such a process is called reversible process. Now, I'm just marking it for you so that, but theoretically, you should keep this thing in mind. Infinite completion time, I do not know how much time it will take to remove those sand particles. Obviously, irreversible is a practical one. It will take a finite time. Practically, it's a one-step process. It will be happening in a cut. Latch removed, cut. It's a hypothetical process. It is a natural process. This irreversible work actually takes place in nature. Equilibrium is maintained at, sir, whenever you remove a particle, equilibrium will exist at each stage. Equilibrium only exists at Initial state and final state. Initial state when latch was there, cut, final state. Now, this is very important. Actually, question only writes this. The question never asks you it is reversible or irreversible. Most of the time, the question hides this reversible and irreversible part and offers you this mathematical justification. They say external pressure is variable. Sir, every time if we are removing one particle, external pressure is getting reduced when the gas is expanding. You can think of the reverse cycle also, as in if this is your initial state, I will keep on adding one particle, so it will get compressed. But if you are similarly for reversible also, you're doing cut, I mean with just a push. So irreversible takes a finite time, reversible take infinite time, either it is expansion or compression. But P external is variable in case of removing slowly. This you have to keep in mind. Whenever external pressure is variable, it is reversible, and whenever external pressure is constant, it's an irreversible process. How constant, sir? You tell me. When the latch was there, what was the external pressure? Atmospheric pressure, maybe. After the latch is removed, what is the external pressure? What is the outside pressure? Sir, external pressure. External pressure at initial state and final state is the same. So, for irreversible process, external pressure is constant. Very, very important point. Now, if you are work done by the gas, you tell me in which case you just become the gas. Let's say I am the gas. Once I am applying pressure, cut. This is the work I am doing. And if you are slowly, I am applying. After a lot of time, I will come up. So obviously, work done during reversible expansion, work done by the gas reversibly is always the maximum work, keeping in mind the pressure of the gas at each stage is greater than the external pressure, because at each stage I had to slightly push. At neither stage it was a point when external pressure was greater. External pressure you will keep on decreasing by removing that particle. So this is a theoretical point you should keep in mind, because reversible work are theoretical work only. It is an ideal case. You do not get these work in real life. They only comes to your pen and paper and JEE asks them. Now, obviously, if you are expanding or you are getting compression, what is the difference between internal pressure of the gas and external pressure? Sir, infinitesimal, the small particle. That is making the difference. So the pressure of gas and external pressure is approximately same. Whereas if there is expansion, the pressure of gas is much higher. If there is expansion, the pressure of gas is much higher. And if there is compression, the external pressure is higher, as in pressure of gas is lower. So if there is compression, the pressure of gas is lower than what? External pressure. So there is a clear boundary set which practically exists in nature. Why you are giving so much reversible, irreversible theory, sir? Moving to the practical side of it. Why I am giving this theory? Now, let us formulate work. Sir, this we know. Cylinder, gas filled, but to the gas pressure, I'll take this gas pressure as P for the sake of simplicity. Volume occupied by the gas is V1. The temperature of the gas is T. Let's say it's a circular cylinder. So this circle, this piston is a circle. This is A, the area of cross section, A. Let us say gas pressure is higher than external pressure. So what the gas will do, sir, it will expand. But you will ask, sir, how it will expand, reversibly or irreversibly? I am taking a general case. How can I take a general case? Calculate small amount of work. So if the gas is expanding to a very small length, let's say dl, it will expand, so its level will rise. Let's say it rises to a length of dl. So can you tell me the small amount of work done by the gas against external pressure? The small amount of work is dw. We do not, to path functions, there is no delta. But the gas has worked to a little extent. So the little value, mathematically we say dW. So therefore, how can you calculate this dW? Sir, work is equal to force into displacement. We know this. What I'm using is your simple 9/10 physics. That's it. Now, sir, if I'm working, the force is acting on me from the top. So this is the direction of the force. But you are expanding in the opposite direction. So definitely the work will come out. Mathematically, physics and maths, physics and chemistry, both thermodynamics are same. I'm proving it away. Although we say work done by the system is negative, but we are not violating the mathematics and logic behind it. Just see. Sir, how can you replace force? Force pressure is equal to force acting per unit area. The external pressure is applied to us. So force I can write as, force can be written as the external pressure into area of cross section, A, into displacement. What is the displacement? Sir, dl, the small length that has been increased. But sir, please put a negative sign. Why beta? Now you can very well see why. Because this external pressure against which the gas is expanding is acting on downside, while the gas is expanding upside. So if displacement and force have an angle of 180 degree, there will be cos 180 will be -1. So this is the small amount of work done. Okay, I'm not making it as equation 1 because I can even simplify this. How? So this is equal to minus the external pressure into area into small length change will be equal to small volume change. Now this is my equation 1 and a very important equation indeed. I am doing one mathematical justification for you. Now you just tell me, if the gases, although I have taken one case, by being mathematically correct, I can even compress. That is what I am taking right now. So let's say if the gas is expanding as of now, with the example which we have taken. So during expansion, final volume, what is change? Final minus initial. So during expansion, what will be delta V? Sir, final value will be, let's say, because it is expanding, let's say it will be 20 minus 10. So it will be a positive value. So during expansion, delta V will be positive. If delta V is positive, P external is definitely a positive value because this sign we have already taken. So during expansion, your work will be a negative value, is what I'm trying to explain you. Mathematically, we are also right. In physics also, when you'll see, they will also be right, but because the frame has been changed, I am discussing my frame because I am dealing with chemistry. Moving ahead. Now, if the gas is undergoing a compression, then what can you say? Sir, if the gas is undergoing a compression, then this delta V, this dV, this volume change will be negative because final, let's say it is compression. Initial change is always final minus initial. Initial was, let's say, 20. Final is, let's say, gas volume 10. So 10 minus 20 is a negative value. So in compression, dV will be a negative value, and this minus will make, therefore dW, that is work, will be a positive value. Now this can be any type of process because I have not considered that whether this P external is constant or not. That is, I am not considering the process is either reversible or irreversible. I do not even care till now because I have just calculated the dW, the small amount of work, and formulated this, that whatever type of work you are, reversible or irreversible, your sign convention will be, during expansion, when work is done by the gas, it is negative, and during compression, when work is done on the gas, work is positive, and so is the sign convention with heat. Now I am dealing with the case. So let us discuss case 1, that is irreversible work. Now, why I have discussed so much about reversible and irreversible process? Because now I will be using the direct conclusion. You tell me, during irreversible work, what was constant? Sir, external pressure. Cut. External pressure initially, also atmospheric pressure, finally also atmospheric pressure. In between, it didn't even stop. So, how can you calculate? Let's say this gas is going from this V1 volume and expanding till this V2 volume. This is the final value, final stage it will reach. So, if it is happening irreversibly, there must be a latch. There must be a latch. It must be stopped. If you pull it out, it will cut, move to volume V2. So that is what type of work? Irreversible work. Now, mathematically speaking, sir, if you have to calculate work, what you have to do? Add that small part. What is that small part? That small amount of work you have already calculated. Now, in order to add what we do, how do we add a variable? Sir, by integrating. From what? Initial volume was V1. Final volume is V2. Put the formula. Therefore, the irreversible work can be calculated as minus P external from V1 to V2 dot dV. Sir, why you have taken P external out of the integration? Because for irreversible work, P external is a constant. Remember, that's why we discussed so much of theory. P external is variable for a reversible process and it is constant for a irreversible process. And hence, I am now direct using that conclusion. So, because it is a constant, so taken out. What is integration of dx? X. So, dv will be v, upper limit minus lower limit. So, this irreversible work will be equal to minus the external pressure into delta V, because integration of dx is x, upper limit V2 minus lower limit V1. So, delta V is nothing but V2 minus V1. Now, one more important thing. Sir, generally, the gas pressure is given in ATM, although it will be given in bar. You can convert bar into ATM. 1 ATM is equal to 1.013 bar. Volume is generally supplied in either liter or ml or cc. We know 1 ml is equal to 1 cc and 1 liter has 1000 ml. You can definitely convert. So actually this pressure volume multiplication is a factor of work. This you have to also keep in mind. And I'm giving you a conversion factor that 1 atm into liter is nothing but 101.3 joule. If you just put these value in of pressure and volume in atm and liter, once you get the answer, whatever sign it will come out to be, because you do not have to keep into consideration that gas is undergoing expansion or compression. You do not have to worry about it. Why? Because V2 is final for us and V1 is initial for us. So if it is compression, the final value will be lesser. So V2 will be lesser. And if it is expansion, V2 will be larger. You do not have to bother. You just put this formula for whatever expansion compression cases come. So what you have to do is final volume minus initial volume. That is it, because change is always final minus initial. After calculating the value in atm liter, convert it into joule with a multiplier of 101.3. Moving ahead to the case 2, which is your reversible work, that is maximum work done by the gas. Maximum work done by the gas, because the question do not generally tells you it is reversible. Over there they say pressure is constant, hence proving irreversible. Over here they ask calculate maximum work. They do not use the word reversible, irreversible. They trick you with English. So that's why I've again written it. Sir, what difference it will make? Nothing. You have to calculate this reversible work done by the gas. It is again, you have to add the packet from volume V1 to V2. Or you can say this reversible work is nothing but minus from V1 to V2. What is dW? P external into dV. Now, I cannot take this external pressure out of integration. What I can do now? Think of the basic mathematics. What is the basic mathematics? Okay, I take this, I'm using this piston. I'm using this piston over here. I'm using this piston over here and drawing a free body diagram of this piston. Can you tell me what is the external pressure acting on this piston? Sir, P external. What is the pressure acting on this piston from downside? Sir, pressure of the gas, to which we have referred as P, pressure of gas. If at all the gas is undergoing expansion, reversibly only, if it is going expansion, then its pressure will be increased. By what? If that one particle is removed, how much extra pressure I can apply? So ittu this much. How can you quantify ittu in maths? An infinitesimally small value. How can you quantify as a dP? Mathematically, small change is dP. Okay. If opposite thing is happening, if compression is happening, sir, I will be lesser. How much? By just addition of that particle. So I'll be lesser, but I will be lesser by this value only. So for any case, you have drawn the free body diagram of that piston. External pressure for any case of expansion and compression for reversible process at each infinitesimally step, small change, it will be P plus minus dP. Because for reversible process, the external pressure and internal pressure is approximately the same. The difference is just that small value dP. It may be added or it may be subtracted. Moving ahead. So, sir, if it is so, I can replace this P external by what? Pressure of gas plus minus dP. So, here I have work done for the reversible process is equal to minus integration V1 to V2. Instead of P external, I am writing P plus minus small change of dP dot dV. Now, you tell me, I am again opening this bracket first. Let us open this bracket first. And approximating, I guess you can clearly see it as well, that this reversible work will be equal to minus integration from V1 to V2 of P dot dV. This P is pressure of gas. Sir, this minus will come and this plus minus may become minus plus, but minus plus of what? Sir, dP dV. What is dP? A very small value. What is dV? A very small value. When both values are multiplied, whatever integration you will do, if this much small values, if compared to a larger value, will be neglected. So I am neglecting, so I'm writing over here, neglecting mathematically dP dot dV factor because it is very small. Remove it. Although the answer that you will be getting will be an approximated answer, but in this way, the derivation has become a piece of cake now. This is the theory thermodynamics has developed for us. And what is pressure of gas? Sir, if it is an ideal gas, P is equal to nRT upon V. Write it. Integration of nRT upon V dot dV. Now, again, I am putting a case for isothermal. I am again putting this case for isothermal ideal gas case. Matlab, that is, over here in the question, it must be given to you that gas is undergoing a reversible change. And what reversible change? Reversible isothermal change. This has to be mentioned. Then only you can use this formula. So it has to be reversible isothermal change. So if it is so, you can write work reversible is equal to moles are constant, R is constant, T is constant. So you will be getting 1 upon V dV. What is integration of 1 upon x dx? Sir, ln of x. What is integration of 1 upon x dx? Ln of x. Put limit, upper limit. So ln of V2 minus ln of V1. Using the property of log, so I can say work reversible is equal to minus nRT ln of final volume upon initial volume. I can also say, remember the property of log, ln is log to the base e. If I want to convert it to log to the base 10, what will be my answer? It will be minus with a multiplier 2.303 nRT log of V2 by V1. Now, this is your important conclusion, but the value again remains the same. If it is an expansion, that is work is done by the gas, work is negative. Or for example, for expansion also, V2 will be larger. So log 1 is a positive value, which will give your work to be a negative value. So that sign convention will be the same. Now, one more case over here. So a star mark for work is during, the question says, uses it, during free expansion. Sir, what is free expansion? Free expansion is when gas is expanding freely. How can I expand freely when there is no external pressure? Sir, there will always be atmospheric pressure. No. That is, I am talking of vacuum. So if gas is expanding in vacuum, that is called free expansion, then in such cases, P external will be 0. Sir, if external pressure is 0, it is indifferent, it is reversible or reversible process, because if external pressure is 0, dW is 0. So if dW is 0, then whatever work it is, either reversible or irreversible, both will be 0. And one thing I have already told you, reversible work is the maximum work. These two things you should always keep in mind. Moving ahead, let us try this question of JEE Mains and let's see you can find the answer. Yes. So now let us try and formulate the value of work. So first of all, let us calculate that what type of process it is. First, let us determine. So we have to calculate work done, okay sir, by the system, okay sir, when it expands from 1 liter to 10 liter. And because it is saying against a constant pressure, that means if P external is constant and that is of 1 atm value, so what are we talking of? We are talking of an irreversible work. So it is simple, I guess. So what formula we will use? We will use formula for an irreversible work, which is equal to negative times of external pressure into change in volume. And we will not bother about it is expansion or compression, because for us change is final minus initial. So we just put the value. So this is -1, which is in atm, whole into the final volume is 10 minus 1. This becomes -9 atm liter. And remember the conversion, it is approximately, by the way, if pressure is in 1 bar and the volume is in liter, then it is exactly 100. The multiplier becomes exactly 100 for converting into joule. But for over here, and because it's an integer type question, so we'll write 101.3. If we will solve it, we will get our answer, which will be coming somewhere around 911 point something, because it will be more than 0.5. So it is 912. Moving forward, what we have is some important points to note now with the derivation of work we have done. So let us at least point these things out. The point number 1 I'm marking is The Q and W, the path functions for float for first law of thermodynamics, are the boundary phenomena, because those are the only ways by which you can change the internal energy of the system. So the boundary that acts as an exchange between system and surrounding are these only functions, which are the path functions of Q and W. The second point, you should always theoretically, because there will be many theoretical questions. You will be getting them in the PYQs that you must be having also. So these theoretical questions have a huge tendency of coming. Sir, why are you not giving all those PYQs? I've included everything in my theory. By giving all those PYQs will definitely make our lecture longer, and our priority is to finish these one shots in the limited possible time, so that we can give you a time of the day which you can definitely invest in your problem solving. So moving ahead to the second note, transactions between system and surrounding occurs till thermodynamic equilibrium is reached. For example, the irreversible process or reversible process, whatever it is, if let's say I'm allowing a system to move from initial state to final state, let's say irreversibly, I've removed the latch and a cut has taken place. Sir, till what point the system will be doing work? Till the point it reaches equilibrium. So what is this equilibrium? Equilibrium in case of this pressure is when external pressure becomes equal to the pressure applied by the gas. So actually every thermodynamic system, when allowed to move by itself, it reaches till a point where it acquires the state of equilibrium. So what thermodynamic equilibrium we will be seeing in our problems are basically three. First is the thermal equilibrium. Whenever heat is exchanging, suppose I have a hot cup of tea in a room, the tea will be getting cold. Till what? It will not be super fridge cold. It will be cooling till its temperature reaches the temperature of the surrounding, the room. So that is called a thermal equilibrium. So when a system reaches a thermal equilibrium, then temperature becomes constant of the system. When it reaches mechanical equilibrium, then pressure of the system becomes equal to that of the surrounding. So pressure at that point of time, what measurable quantity becomes constant? Pressure. And if it's a chemical reaction, then obviously the concentration of reactant of the reaction mixture will become constant, as we have already seen in chemical equilibrium. So these are the basic thermodynamic equilibrium which a system reaches when allowed to move by itself. Now, third point, some theoretical point you should keep in mind. Yes, this is important. Internal energy is summation of all possible energies of the system except one, gravitational energy. You should always theoretically keep this thing in mind. Gravitational energy do not contribute to the internal energy of the system. And at last, since we have said internal energy is a function of temperature, and for isothermal process, internal energy change will be zero, but this is only valid for ideal gas. Advanced have generally played with this logic of students. So you must keep this thing in mind, that this thing is only valid for gases. For other states of matter, you cannot say that internal energy is only the function of temperature. It may include some other variables also. So these 4 points I have made you note. And moving ahead, so I guess this is the simple questions. Let us try and do them. The question says, during compression of a spring, work done is itta. Okay, work done is 10 kilojoule and 2 kilojoule escaped to the surrounding as heat. So what is the value of Q? 2. No sir, -2. Why? Because anything that comes out of the system, in chemistry it is with a negative sign, and anything heat or work goes to the system, it is with a positive sign. And since we are doing work done on the system, that is 10 kilojoules, so W value is plus 10 for us. Remember, unit is kilojoule and answer is also asked in kilojoule, so it's no big deal. Just applying float. What is float? Delta U is equal to Q plus W. See, only on this a mains question was asked. So what is Q, sir? -2. What is W, sir? 10. Remember, unit is kilojoule. So this is definitely 8. So your answer will be, delta U will be 8. I have already given the answer. Moving ahead. Again, a 2017 mains question. The question says delta U is equal to, just this question, and the options are given. Delta U is equal to, sir, by float we know, delta U is equal to heat plus work. Now, it's an isochoric work, sir. If you want to relate U with W, then Q should die. How can Q die? Q can only die when its value becomes 0. When does heat exchange between system and surrounding become 0, sir? During adiabatic process. So delta U can become equal to W. So internal energy is equal to work when Q is 0, and Q is 0 during adiabatic process. So delta U is nothing but adiabatic work. This is how English plays with your little mathematics. Moving ahead. A piston filled with 0.1 mole of an ideal gas, so these are moles of gas given to you, expands reversibly. Now this is a reversible process, so the formula for work that you will be using will be reversible work. Mind you, let us remember the formula again. It is minus nRT ln of V2 upon V1. And since at times you will get this type of questions as well. Sir, what type of questions? Since it's an isothermal process, so if T is constant for a gas, for an ideal gas, I can definitely say P1 V1 becomes equal to P2 V2. So although we have remembered and learned the formula in form of V2 by V1, but this V2 by V1 can also be equated as P1 by P2. Although this thing will not be used in this question, but it just clicked to my mind. So I am giving you this formula as well, that for reversible work, if pressure change is given, then you can use pressure change also. But for that, the ln value will be P1 upon P2, because V2 by V1 can be equated as P1 by P2. Moving ahead. So the volume is changing from 50 ml to 375 ml. So this is the value of V1 and this is the value of V2. So N value is given, V2 value is given, V1 value is given. At constant temperature of 37 degrees Celsius. In Kelvin, this temperature will be, so T will be equal to 273 plus 37. So this is 310, I guess. Just check. So this is somewhere around 31. Yes, this is 310 Kelvin. So T value also know. As it does so, it absorbs 208 joule of heat. Okay. During this, it absorbs, as in Q is equal to plus 208. It is in joule only. The value of Q and W for the process. Hey? Sometimes the question asks you very simple question but gives lots of vague information. What is vague? Which is of no use for solving that particular question. Like over here, the question is giving you too much of data, but what is asking? It is asking you the value of Q and W for the process. Sir, Q it is already giving. The only thing the question wants to ask from you is whether this Q will be plus Q or minus Q, because the system is absorbing, so Q is plus. So this is plus 208. So either A option will be correct, this is wrong, or D will be correct. Let us check with work. Sir, but it's an ideal gas at constant temperature, so you do not have to apply float also. Because whatever work you will be receiving, this reversible work, you do not have to, although you can labor and work hard and calculate this value, but not required. Why, sir? Because by float, by first law, I know delta U is equal to Q plus W, and for isothermal process, and since this temperature is constant, so it's an isothermal process. For isothermal process, delta U is always 0. For an ideal gas, not always, and this is an ideal gas given in the question. So if delta U is 0, so Q becomes equal to minus W. So whatever heat you will be giving to the system will be directly doing output work. So work done by the system is minus, because you can see with the formula as well, Q is equal to minus W. This is also direct theory question. So this is your answer. The answer is option A. I guess I've given the answer as well. Yes. So moving ahead, and let us continue the discussion with another thermodynamic variable, which is enthalpy. Now, why it is required? Because practically what reactions in chemistry we are familiar with, they take place in open atmosphere, that is at constant pressure. So generally what we encounter is reactions and processes and systems at constant pressure. So how can we accommodate that constant pressure thing? That's why we are defining this new variable. Again, enthalpy also signifies energy of the system, but it is internal energy of the system plus some extra pressure volume work, because now we know pressure into volume is also a mechanical work capacity of a system. So we add these two and mathematically defined this as enthalpy. Again, that it is difficult to determine absolute value. I am not asking you to determine absolute value. I'm just defining this absolute value of H is equal to U plus PV. Like all thermodynamic property, it is also extensive and a state function. Sir, so let us do what we have done. Small change of delta H will be equal to small change of internal energy plus small change of pressure volume work. Simple. After this, sir, or for a large change, I can also say delta H is equal to internal energy, large change plus delta PV. Now, my friends, this is the formula which is always applicable because I have not given it any condition. It is a generalized formula. So let me again write this generalized formula for you, and I want you to keep this thing in your mind. Very important. Always applicable. What is always applicable, sir? Delta H is always equal to delta U plus. Let us write this delta PV as final product is P2 V2 minus initial product is P1 V1. So this is a formula, although very less used, but is always applicable. Sir, less used because I recently said that why I am defining enthalpy at first place. Sir, we are defining because generally systems are present at, so systems are at constant pressure, as in external pressure is atmospheric pressure, then pressure is constant. Sir, nothing to worry. P is constant. So if this P is constant, it will come out from the differentiation or the change part. So what formula you will be having? Sir, it is no big deal. Delta U plus P delta V. Now this is a formula you will be encountering and using more for your questions. So general is that one. Precise is, precise as in precise by being taking the pressure to be constant. Now, this is the most used because chemistry we will be having chemical reaction. So when you are given ideal gas, sir, why ideal gas? Because for solids and liquids, the PV work contribution is almost negligible. So again, I'm writing this also because this is also a very important point, that for solids and liquids, for these both states of matter, their capacity to do pressure volume mechanical work is negligible, 0. If you try to grab my neck, I'll say negligible. So what I'm saying is for solids and liquids, because this mechanical work is approximately 0, so delta H is approximately equal to delta U. This thing also you should theoretically keep in your mind, asked in the questions a lot of time. But sir, if I have gases, that too ideal gas, because for ideal gas we can apply PV equal to nRT, and they are participating in a physical change or a chemical change, that means they are undergoing some change. Sir, how will you define a change? A physical change like H2O liquid is undergoing H2O gas, although it's a physical change. But you can write delta N for this reaction. Just like we have introduced this delta N, what is a change? Sir, final minus initial. So for a reaction, what is a change? What is finally produced? Product minus reactant. And what contributing states you are only bothered with? Sir, only gases. And gases, what are you considering? Ideal gas. So for this physical change, can you tell me the value of delta Ng, sir? Very easy. Product is 1 minus reactant is solid liquid. I am not bothered, so I am 0. So delta Ng is 1 for this. Can you tell me delta Ng for any such gaseous reaction? I'm just writing a general reaction. Let's say A mole of A plus B mole of B forming C moles of C and D moles of D, and I'm considering all of these species are in which state? Gaseous state. So you tell me the value of delta Ng for such reactions will be, delta is change is final minus initial. Final is what? Product. What are product coefficients? C plus D minus what are reactant coefficients? A plus B. So this is how you calculate delta Ng, sir. But we can calculate delta Ng. What we will do with that delta Ng? Nothing. Apply this basic formula. Delta H for such ideal gases undergoing change, what will be the formula? Delta H will be nothing but it will be equal to delta U plus change of what? PV. For ideal gas, what is PV? Sir, nRT. So put that nRT. Why bothering? This is nRT. What else? Sir, or I can say delta H is equal to delta U plus, if temperature is constant, R is always a universal gas constant, so I can write it as RT will come out to be constant of this change, and this change will only be having delta N. But whose delta N I am considered with? I am bothered with of gases. Hence, already told you about delta Ng, and this formula will definitely give you one question. It's the feeling for this January JEE mains. So this is how you calculate enthalpy and entropy for a gas moving. Now, whatever we have done, a simple question based on that, let us try and attempt this. For water at 100 degrees Celsius and 1 bar delta H, delta, okay, the difference, see, the same question is asked. Now, the delta H minus delta U is given, but it is of vaporization. Sir, how can you write reaction for vaporization? Vaporization mean H2O liquid, because it is talking of water, is changing to H2O gas, that is vaporization. Can you tell me the value of delta Ng? Sir, it is pure liquid. Pure liquid has, it will not come into consideration because we just have to calculate the value of delta Ng, and this is not gas. This is the gas. So what will be the value of delta Ng for you? It will be 1 minus 0 because I do not see any gaseous reactant. So delta Ng is 1. How can you formulate delta H minus delta U, sir? It will be equal to delta Ng RT. Delta Ng value we already know it is 1. R, I guess it is given. R is given to be 8.31. And what is the constant temperatures are 100 degrees Celsius as in 373 Kelvin. So if you just try to solve this, you will get your answer. I have already written the answer. It will be, yes, you have to change it in scientific in this term. So 10 raised power 2 you have to keep separately. Moving ahead, you can now one theory is also written over here. Sir, the question is saying you have to assume that volume of liquid water is very small. Why it is written? That if gas is occupying a volume and let's say if liquid water is also present, then volume available for the gas will not be complete V. That's why the question is saying no, liquid water is applying negligible volume. So you can definitely take the complete volume. That means you do not have to bother while applying the formula, although we haven't applied, but in the derivation we have done PV equal to nRT. So the V available for the gas is not complete V. If water is also present, then a volume available for the gas is not complete V. So that's why question is saying, no, you do not take any tension. So even if you do not read this, you will be solving the question by the same logic. But some advanced question may grab you onto this. That's why I'm explaining, although not required for this question. And assume H2O gas to be treated as an ideal gas, as in for H2O gas also you can apply PV equal to nRT, because practically speaking there is no ideal gas in nature. So if you are applying PV equal to nRT for any gas, that is you are assuming the gas to be ideal. That's what question. Even if these things you will not be knowing, still you will be doing the same thing because you are assuming the same thing by itself. Moving ahead. Next question, again a JEE question on the same formula. I just want to show you that whatever theory I am giving, the theory will definitely make you a question. So what you have to do, read and then go and attempt the PYQs and the sheet. Difference between deltas are same, but just now over here you have to write the reaction. So what is the reaction? Combustion. Combustion of what? Heptane. What is heptane? Because I guess every one of us is at least 10th pass. So heptane is a 7 carbon alkane. 7 carbon as in 7 2 ja 14 plus 2 as in heptane is NH2n plus 2. 7 2 ja 14 plus 2 is 16. What does combustion mean? Reaction with oxygen. What does it forms? CO2 and H2O. Just do the stoichiometry. Because I have 7 carbon here, so I will be getting a 7 here. Carbon is balanced. Hydrogen, I'm having 16 over here, so I need 8 hydrogens over here. 16 done. Oxygen is 14. 14 plus 8 is 22. So I need 11 oxygen over here. This is how you write the combustion reaction. Just check. 7 2 ja 14. 14 plus 8 is, yes, this is right. 22, so I'm writing 11 over. Now, sir, we have to calculate delta Ng. In question also it is given heptane is a liquid, so delta Ng, heptane will not contribute. What else? Sir, the temperature, okay, the difference between delta and combustion of 1 mole of is carried out at a temperature. The temperature question is not telling us, but it is telling us heptane is a hydrocarbon and is present in liquid state. That means temperature is not very extreme. So if temperature is not very extreme, then it is normal. So if it is normal temperature, will H2O be gas? No, sir. It will also be a liquid because heptane is a liquid. If temperature would have been in extreme conditions, more than room temperature, even heptane can't be in liquid state. Therefore, this water also, now this is most tricky part of the question, that these water are not water vapors. Because heptane is a liquid, so heptane, if an organic compound which has less attraction force is a liquid, so water being hydrogen bonded will definitely be a liquid solvent at that particular temperature. So this is a catch you can obtain through the inorganic and chemical bonding knowledge of yours. So this is the tricky part of the question. So can you tell me the value of delta Ng? Yes, sir. 7 minus 11. So 7 minus 11 is how much? 7 minus 11 is, okay, minus 4. Sorry. This is minus 4. So value of delta Ng we know. So what will be its value? Minus 4 RT. And you just have to tick the answer. C is your answer. Moving ahead. Let us try and discuss about this another extensive and path function property of heat capacity. Heat capacity, as the name only suggests. Sir, suppose we have a system. Let's say this system has some m gram of matter with n number of moles inside it. So if I want to change the temperature of this system by 1 degree, how much heat I have to use? dQ, the small amount of heat. So for 1 degree temperature change, how much heat I will be using will be its heat capacity. Again, let's say in order to change the system, change the temperature of system by a small value of delta T, I am supplying a small amount of heat of dQ. Example. So if I wish to change the temperature of the system by 1 degree, the heat that I have to give to the system will be dQ by dt. Simple. And this ratio, my friends, is called the heat capacity. So this heat capacity, if we try to find the average change, this small dQ will become Q because no delta Q for us. And this dt becomes delta T. So this becomes nothing but heat capacity. But it's an extensive property because a type of heat. Can you tell me its unit? Definitely, sir. Its unit will be joule per degree Kelvin or degree Celsius because it's a change. So it is, we are indifferent. Even in 1 degree Kelvin change, 1 degree Celsius scale change, both are same. So either value. Now, mathematically, where question tricks you is, for mains, this is more than sufficient. But mathematically, so I'm putting it inside a box because this knowledge is more than sufficient, but some extra thing. How mains can trick you is, if you just look at the smaller value, you can definitely see, sir, dQ is nothing but heat capacity dot dt. And if it is a variable, how will you add the variable, sir? You will integrate. Initially, how much heat I have supplied? 0. Remember, no delta Q for us. Initially, what was the temperature at state 1? Let's say T1. How much heat I have supplied? Let's say, sir, Q. What the temperature changed? Let's say T2. I'm just generalizing it. You can either do this. If this Q is minus, then you are taking that heat from the system. So T2 will be lesser. So we do not have to bother, just like in case of work, that whether it is expansion or compression. So we do not have to bother that whether we are giving heat to the system, taking by the sensor. The Q sign will take that into consideration. So I'm using change. For 1 degree change, what amount of heat has to be exchanged is the heat capacity of the system, obviously. And how question can trick you is integration of dx will always be x, upper limit minus lower limit. So this will definitely be a Q value, but this I'm not doing anything and keeping it just like this, so that even if some good question comes, you can know its general formula which is applied every time. Because here I have considered C to be constant. Like over here, if you consider C to be constant, then it will come out from the integration. If it is constant and not depending on temperature, let's say if it is a function of temperature, then mathematically you have to differentiate. So let's say if C is constant, it will come out, then integration of dt will become T, upper limit minus lower limit, so it will become delta T. So this is a special case which we have already considered when C is a constant. And generally for means it is a constant. But still I am giving you the general formula also. Now, moving to the application side of heat capacity, you can very well see, sir, heat capacity is extensive because it's a heat will depend on the amount of substance. But sir, extensive upon extensive become intensive. With what I am trying to divide with this mass and moles. Let's say this system has m gram. So for m gram, what was the heat capacity? C. So for 1 gram, it will be C upon m. So to the value of C upon m, I am referring to as S. So this S will be equal to C upon m. So it will be intensive, extensive upon extensive becomes intensive, simple. Similarly, this n moles of substance, how much? What was its heat capacity? Sir, C. It has m gram or n moles, whatever mathematical nomenclature you can use. So for n moles, if it was C, then for 1 mole it will be, sir, C upon n, and to that I am referring to as molar heat capacity. That's it. What will be its unit? C we have already defined. What is its unit? Sir, unit is also simple. Its unit will be joule per gram per Kelvin. Sometimes, this you have to keep this in mind. Question never gives you the exact name. Technically, it is called specific heat capacity. You know what questions does? Question just write heat capacity, but it tells you the unit of the value. So with unit, you will be able to check that what exactly type of heat capacity is given in the question. So make sure that you look at this unit very religiously. Sometimes this can be either be per gram, per kg, then you have to put this mass in kg, simple. Over here, sir, its unit will be joule per mole per Kelvin. Simple. Sir, why am I not telling more about this? Because we need to have special cases of molar heat capacity is generally used. And molar heat capacities, for them, we use special cases. And in order to understand those special cases, let us first know, we'll define heat capacity, molar heat capacity at constant pressure. To that C we'll write as Cp. Molar heat capacity of a system at constant volume, to that we refer as Cv. But before deriving the relationship between Cp and Cv, because we know molar heat capacity, so we know Cp and Cv. When we calculate molar heat capacity at constant pressure, it is Cp. At constant volume, it is Cv. But before defining that, let us understand the heat exchange between system and surrounding at constant pressure and constant volume equals to what? Just very easy derivation. Just pay a few seconds and a thought over here. First, enthalpy. Can you tell me what is enthalpy? Sir, enthalpy is equal to internal energy plus pressure volume work. So can you tell me what is small change of enthalpy? Sir, dH is equal to small change in internal energy du plus small amount of PV work dPV. What is integration of differentiation of xy, two variables? Sir, by parts we do. How do you do by parts? Sir, dh is equal to du plus p dv plus v dot dp. Now I am putting a case. The case, till now I have not put any case. This was a general derivation. Now I am saying at constant pressure. Now I am taking pressure to be constant. Now if pressure is constant, this factor will be gone. Pressure constant, dp gone. And from first law of thermodynamics, we know small internal energy change is equal to small heat exchange plus dw, and to dw you write p dot dv. If you use this du over here, let's say this is equation 1. So I can have dh is equal to, instead of du, what I'm writing? dq. Sir, minus pdv. Sir, plus pdv. Cancelled. This is already cancelled. Oh, sir, we are left with this only. Yes. So this is small change. Can you tell me? Can you? Acha, do not tell me. You integrate. Sir, let's integrate. Initially, how much heat I have given? 0. Finally, how much heat I have given? Q. But this Q I am referring as QP because I am giving heat to the system at constant pressure. Now I am defining that constant pressure, giving heat to the system at constant pressure, and hence writing as QP with the P in subscript. What was the enthalpy of the system initially? H1. After giving this much of heat, it changed to H2. I am not asking you to be focused on the absolute value. Do not be focused, my friends. But at least be focused on the derivation. What is the integration of dx? X. dh, upper limit minus lower limit is dh. And it becomes equal to QP. A very, very important observation indeed. That is, heat exchange between system and surrounding at constant pressure is equal to delta H. Remember this. Again, I am doing one more derivation. But this derivation I am doing for another system. Let's say for isocoric system, as in system is present at a situation when volume is not changing. So for such a process, by float, what can you say? Sir, for any process, I can say du is equal to dq plus dw. Sir, if it is an isocoric process, volume is not changing. If volume not changing, what is work? Small work. Sir, minus p dv. Sir, v not changing, so dv is 0. So any kind of work becomes 0. So if work becomes 0, internal energy change will be equal to heat supplied. Integrate it. From U1 to U2, initially I have given heat 0. At state 2, I have given heat, but this heat 2 I am referring as QV because this heat I am exchanging with the system at constant volume, isocoric. Just tell me what the derivation gave you a conclusion. Sir, it gave us a conclusion that delta U is nothing but heat exchange between system and surrounding at constant volume, and this is the other conclusion I am drawing from this. Hello. Now, using these two conclusions, and since I know the formula of molar heat capacity, it is equal to C upon N. Let us put the value of C. So this Cm will be equal to, this C is nothing but Q by delta T. This is nothing but dq upon n dt. I'm writing generally because this is always true. That is true when molar value is constant. So I'm over here, this is a general formula. So if I know this, that, or I can say dq is equal to molar heat capacity into moles dot dt. This also I can conclude. Hello? And if it is so, I can integrate it. Let's say initially I have done 0 at time t, finally it is q. So what is integration of dx x? So here I'll directly get q. If moles are constant, if heat capacity is constant, I'm considering them to be constant because mains question, more or less advanced question also. This molar heat capacity, they give you to be a constant value. So two constants coming out. So NC, the molar value, hence writing M over here just. And what is integration of dx x dt t, upper limit minus lower t2 minus t1. So directly writing delta t. Can't you see a formula over here? So if this heat is exchanging at constant pressure, it becomes QP, it becomes CP. If this heat is exchanging at constant volume, it becomes QV, it becomes CV. Using this conclusion over here, because now we know what are these CP and CV. So using over here only I'm using. Now I know this QV is equal to delta U, and it is nothing but NCV delta T, your first conclusion. And QP is nothing but delta H and will be equal to NCP delta T. After knowing these two very, very important relationships, again apply this in definition of enthalpy. Also, I know delta H is equal to delta U plus delta PV. I know that. So for 1 mole of ideal gas, PV is equal to RT. So I can say delta H minus delta U is equal to, instead of PV, I'm writing RT for 1 mole because R is constant. So it will be equal to delta T. This is for 1 mole ideal gas. I guess delta H you know how to write. Delta H is nothing but NCP delta T. Delta U is nothing but NCV delta T, and delta T, or else if taking 1 mole here, then assume 1 mole here also, or if not taking 1 mole here, then N will also be there. So this will be N delta T. But since I have written 1 mole, so let us kill that mole. So make this N also 1. So for delta H, what I can write? For delta H, I can write N gone CP. Delta T also I have written, but I am cancelling it in mind. Delta T gone. Minus CV, delta T gone, and this delta T gone. So what will be left behind? R. So these are some results. This one slide is full of derivations for you. Please, please, please write these direct numericals, direct formula in your copy because these questions will come. Moving to now. No. Because we have dealt with the heat capacities, let us formulate certain things now. Sir, what? See, for solids and liquids, delta H is approximately equal to delta U. So for solids and liquid, delta H is what? Delta H represents CP. Delta U represents CV. So for solids and liquids, CP and CV will also be approximately same. And how you will calculate there, see whatever like the heat capacity you calculate. How you calculate heat capacity, keeping that heat capacity to be constant. I mean the basic mains formula, sir, heat upon delta T. Right? Now, sir, if the process is isothermal, what can you comment about heat capacity? You comment about heat. Process is isothermal, so delta T will be 0. So whatever the value of heat capacity the system will be having, it will be tending towards very infinitely large value. Theoretically, you should know this. For adiabatic process, array sir, what are you doing? Adiabatic process Q is 0, so C will be tending to 0. For isobaric and isochoric process, I have already defined CP and CV. Now, the ratio CP-CV is also of great importance to us, and hence it is also represented by the symbol gamma. In physics thermodynamics, the adiabatic, this gamma, you will be using a lot. We will also be employing it for a bit, but in the later slides. But for the time being, you should know value of CP by CV is gamma. Now, because states of matter chapter has been removed from our syllabus, so I'm just summarizing because mains is not at all interested in this thing, but still summarizing with a very short summary. Actually, what gases do, why does gases possess energy? Because of n number of factors, but basically what is their most contributing energy? Sir, their kinetic energy. But actually the kinetic energy possessed by gases is contributed due to lots of collisions and lots of motions. The translational motion along x-axis, y-axis, z-axis, that also depends upon their shape, their rotational motion, their vibrational motion. So generally, all these types of degrees of freedom which a gas has in order to attain kinetic energies is accounted by law of equipartition of energy. Sir, not feeling confident, leave it. What I'm saying is gas has got number of kinetic energies possibilities, and that possibility of the freedom of gas in moving in the world is designated by the word degree of freedom. So this degree of freedom gives you the total number of modes and methods by which an ideal gas molecule can exchange energy during collision. And we are talking of their kinetic energy, the various types of kinetic energy. So summing about, sir, what internal energy of the system you have already given in the formula in the previous slide, 3 by 2 RT for 1 mole, and for n moles 3 by 2 nRT, remember? Sir, was it wrong? No. But over there, the KTG, kinetic theory of gases, people have considered gas only to be a molecule, one molecule. So it is valid for a monatomic gas. Let's say if I am linear or if I have different shapes, my types of degree of freedom, that is my types of modes of colliding will change. Do not give much focus on that because it will be, that is law of equipartition of energy, although that is not very difficult, but it will be taking a bit of our time and we are not interested to invest the time over there. So what I'm saying is, what is the value of internal energy for us? Let us directly go to that internal energy first. So I'm calculating the change in internal energy of the system as per type of gas present. Previously, we were not interested in type of gas. So we are just modifying that formula. How? We are saying that change in internal energy is equal to definitely yes, number of moles into R into T. That is, still I'm saying for ideal gas, internal energy is a function of temperature. I'm not violating that. But instead of that 3 by 2, what I am saying is you should now remember is F by 2. Everything remains the same. The only thing I am changing is instead of 3, I'm writing this degree of freedom. Because that 3 was only written as considering, assuming that the gas is just a molecule, one molecule. Sir, only like helium. Helium is just a molecule, a monoatomic gas. So for helium, is it true? Yes. So that for this F, I'm relating you with this table. So for monoatomic gases, whatever you thought was right, it is 3 by 2 because these are all statistical facts. For diatomic gas, the F you will take as 5. For polyatomic also you will take at 5 as 5, but the polyatomic gas as in having more than 2 atoms because diatomic is having 2 atoms. Diatomic atom will always be linear because 2 points can only be joined through a line, so it has to be linear. Polyatomic, if linear, then linear thing will have same degree of freedom, same possibilities of motion. But if I become non-linear, value of F increases by 1. So monatomic 3 like for helium, for diatomic gases like H2, O2, N2, it is 5. For linear gases like CO2 shape I have drawn, it's a linear molecule, polyatomic, but still because linear, so 5. And for whatever gases, ozone, SO3, SO2, whatever gases whose shape as per chemical bonding are not linear, their degree of freedom contribution is 6. So in place of this formula, my friends, what you will write? You will write F by 2 into nRT. One more thing, not much use, but just telling you again, what is this? This is internal energy for one mole of gas was this. For n moles of gas, it is this. Can you tell me for one molecule? Arey sir, it is easy. For n moles, you are saying internal energy is F by 2 into nRT. Actually, I am focusing on this value of R because what is, let's say, for 1 mole, you just tell me for 1 mole. So for 1 mole internal energy is F by 2 into RT because N is 1. So can you tell me this value for 1 mole? So for 1 molecule, I'm sorry. So can you tell me this value for 1 molecule? Yes, sir. 1 mole is Na molecules. So Na molecules has this much of internal energy, F by 2 into RT. So for if Na molecules have this much energy, 1 molecule will have this much upon Na. So for 1 molecule, this value will be equal to, let's say I'm saying delta U dash, F by 2 into R upon Na times of T. And actually, this was also statistically calculated by a scientist, and this is separately represented as K, and this is termed as Boltzmann constant. Boltzmann constant. Its value is nothing but value of R upon Avogadro's number A. This Avogadro number is same, 6 into 10 raised to power 23. You should keep this thing in mind. Very less use, but still telling you because it's a note point. Moving ahead. Now, after moving ahead to a question, so let us directly try this question from mains 2019. The question is, if you see practically, the question is simple. See how. For silver, sir, silver is a metal, so it must be a solid. Okay. So for silver, Cp as in heat capacity at constant pressure is given. But sir, it is not given to be constant. It is given as a variable. So this Cp is 23 plus 0.01 T depending upon temperature, not a constant. If the temperature T of 3 moles of silver is raised from 300 Kelvin to this much Kelvin at constant pressure, okay, because it is defining Cp, so pressure will definitely be constant. You have to tell me the value of delta H. So sir, write that formula generally, okay. We know delta H is nothing but NCP dt. Sir, but why you are taking dp? Here you are taking delta H. Okay, I am adding it. How do you add a variable? Sir, you have already told us. You have to integrate. From what? From T1 to T2. Whatever constant will come out. Now Cp is not constant. Hence using the general formula. So what will be your answer? Sir, delta H is equal to N will come out. So how many moles you have? 3 moles. But sir, Cp is not a constant. So let us integrate it. It is 23 plus 0.01 times of T dot dt. And limit is from 300 Kelvin. You have to raise the temperature from 300 till 1000. Now this is just basic maths for you from now. What we will do? Sir, nothing. Integrate. How to integrate, sir? I am helping you if you are not comfortable with it. 3. Sir, what is the integration of 23? 23 is a constant. So it will be 23t plus 0.01 of what is integration of x square upon 2. So t square upon 2. Upper limit minus lower limit. Now this mathematics you have to follow. Put t as 1000 minus put t as 100. This thing you have to open the bracket, solve, multiply it by 3. Whatever answer you will be getting, that will be in joule. The question is asking you to report the answer in kilojoule. Options are there in kilojoule. So this mathematics now you have to do very religiously and you will land up with the, option A. So moving to the next question, you guys attempt and I sip just some water. That these are just same questions. You must have attempted. I have sipped water. The combustion of benzene. What is benzene? Benzene is, sir, C6H6. Combustion is reaction with combustion is reaction with oxygen. Will produce, sir, I'm directly writing 6 CO2 because 6 carbon, 3 H2O because 6 hydrogen. Oxygen, how will I balance? So 12 and 2, 15. So this will be 15 by 2. I'm writing it clearly because there is some hodgepodge over there. So 15 by 2 O2. Now, what state benzene is in? Sir, not good, not considerable for us, liquid. What about water? Say 25 degrees Celsius, liquid. So again, see, again mains is asking this water has to be in liquid state types thing. So what will be the value of, what is, 15 by 2? Sir, 7.5. So what is delta Ng for this equation? So 6 minus 7.5. So minus 1.5. That's it. So combustion is taking place, the heat of combustion of benzene at constant volume. So this is the value of delta U. How much? Minus 3263.9 kilojoule. Remember, value kilojoule, unit dimension, unit dimension. Heat of combustion in kilojoule only you have to find of benzene at constant pressure. That means I have to find delta H. Delta H is nothing but delta U, which is 3263.9 plus delta Ng. What is delta Ng? Minus, so it is minus 1.5. It is value of delta Ng. What is R? R you have to take as 8.31. Or you have to do again calculation into T. 25 degrees Celsius. Oh my God. So this is 298 Kelvin. Acha. A, you do not have to do calculation. Why? Think. Options are given. Sir, you do not have to take up your pen also. Why? Value is 3263.9, 3264. A value is getting subtracted, so it will become more negative. So answer should be by magnitude must be higher than this, but with a negative sign. Why calculate? This is a positive value, not an answer. This is a positive value, not an answer. 50% even Jai Shri Ram, but do it. Minus, sir, it has to be in magnitude greater than 3263.3264. So this is without calculate. See, it is greater. 3267. It was 3263. So I have only one option. You can calculate also, but I guess you will be finding the same answer. Moving ahead. Yeah. So moving forward to the zeroth law of thermodynamics. It is nothing but a general FYI type of thing for you. Not much important, but still, because some people think, sir, you have not taught that. So just for FYI, just for an information, it's a common sense. Suppose I have this system A and this system is in thermodynamic equilibrium, let's say with this system B. Sir, if both these systems are in thermodynamic equilibrium, remember thermodynamic as in temperature of both these species will be same, both these systems will be same. Now let's say if I'm considering another system C, which is also in thermodynamic equilibrium, but with B, then temperature of B and C will also be same. So what zeroth law of thermodynamics says, if A and B are friends, equilibrium, thermal equilibrium, B and C are friends, thermal equilibrium, then A and C will also be in thermal equilibrium with each other. So this is just an FYI information for you moving forward. Yes, so let us just move forward for the discussion of comparison of reversible and irreversible work, which we have already done, but let us quantify that through some visual graphs. Now, as I already discussed that reversible work is more than irreversible work, but during what? Expansion or compression? So let us now understand that, because we have done quite a bit of mathematics also till this point of time. Now what I'm saying is, one thing you should always keep in mind, because after so much of mathematical understanding through previous slides, we can definitely say, sir, P into V is a work. So whatever graph under P into V, area under curve, will definitely mathematically will give you the multiplication, that is work. So now we know, sir, area under PV curve can also give us work. So we can easily visualize that area and we can find that which type of work is more. Now, this is the first case where I'm considering the expansion. From point A to point B, gas is expanding, as in you can see volume is rising. Let's say this value is V1 and it is rising and reaching a value of V2. Sir, how you are saying it is reaching? Because A is my initial point and this graph is going from A to B. So volume is increasing, pressure is decreasing. Sir, so what type of process is it? It can be any process. It can be isothermal, it can be adiabatic. We'll see just in the later slides that adiabatic also has a similar curve like isothermal curve. The slope is gradient is different, but we'll discuss. So it can be adiabatic because both have a curve nature as isothermal as adiabatic. So it can be any expansion. Now, sir, what is work done? Because gas is expanding. So gas is expanding, it will be work done by the system. Okay, value of W, whatever value it will come out, value will be with a negative sign because this is work done by the gas. I'm not what that we have discussed. I am now comparing the magnitude. You tell me work done in this reversible process, I'm marking as the green area, which is area under curve. So work done by a reversible, work done reversibly during expansion of an ideal gas is more. We have read it. It's the maximum work. So now let us visualize it. How do you do irreversible work? We say during irreversible work, pressure, external pressure is constant. For example, I'm explaining an expansion. Let us say there is a latch. This pen is a latch. If you remove this latch, my hand, let's say this latch is removed. Cut. I'll move, expand instantly. Now you tell me what is the time when I have started? What was my time t equal to 0? This. But process does not start. The fraction of second after which this latch is removed, I'll cut. So point is, external pressure is the same which the gas has attained finally. Initial, you will say, sir, externally the pressure is same. And what about the pressure of the gas? Sir, because it is happening in an instant, in a jiffy, so pressure whenever from time t equal to 0, pressure directly reaches to that maximum value is what I am trying to explain you through graph also. That since irreversible process happens in a jiffy, cut, you tell me, I have expansion, I have opened the latch, cut, directly the pressure will drop down from point A, directly the pressure will drop down and will reach this value. So pressure from value P1 will directly drop down to value P2. You can see P2 is less. And what will be after this volume will be increasing. So you tell me what is the area under curve for this white thing? What is the white thing? White thing is the irreversible process. As soon as I have opened the latch, pressure cut is because volume is increasing, so pressure will decrease. So it decreased in that instant only. So what pressure it reached? Sir, directly it reached P2 and then expansion has taken place in this constant pressure. So sir, that means this is the constant pressure that we will be placing in the calculations. Yes, this is the constant pressure that you are supplied with. So point is, what is area under curve for this reversible process? This white area. This is, irreversible process because it is happening in an instant. So sir, now we can very well see this green area is more. This white area and green area is common, but this green area is more. So that means reversible work is more in magnitude than irreversible work. A very beautiful thing to observe. Now, if I'm doing compression, volume is getting decreased. I'm starting from here and I'm decreasing volume as in increasing pressure. Now, the first thing again the same. What is, because this is the graph. So, what is area under curve? So, this one. Okay. So, you very well see the work of a reversible process, area under curve, the magnitude. Now, this is the other case, not the same one. So I'm separating it by, or you will say, sir, both are same, na? This is the conclusion of this. Reversible work is more than irreversible work during expansion, isothermal, adiabatic. But now, compression. This is isothermal or adiabatic. This was expansion. So this is compression. Now, this we understand, sir. We can see the green area. It is the reversible work. Now show us the irreversible work. Let me make it again white. Now, you tell me, I am starting from point A. The moment I am compressing, again the pressure will be changing in a cut, in a jiffy, and will be reaching to this higher value. So the pressure has reached to this point, and after reaching to this point, now the volume is getting decreased. So you tell me, what is the area under curve? Sir, this is obviously there, but this point will this area under curve will also be added. Obviously, it will be there, because now my graph is starting from here and reaching till here. So this is my area under curve. So obviously this area is this white portion. I will be acquiring this green also. I am deliberately not pointing it out, or else whenever you will take this PDF also, it will be much easier for you to understand that it will be this area also and this area also. So you can definitely see what work is larger. Sir, irreversible work. So magnitude of irreversible work is greater in magnitude when we are dealing with compression. Very important thing. Keep this thing in mind. Moving ahead. Now, some JEE mains question. The question says 4 liter of an ideal gas. Okay, you have its volume. It's V1. Is allowed to expand. Okay, you are expanding into vacuum. Sir, what is vacuum? Vacuum is when P external is 0. If P external is 0, dW is 0. So any type of work is 0. Reversible, irreversible, I'm indifferent, because dW will be 0. So if packet is 0, if we'll integrate it reversibly, irreversibly, it will be 0, done many times. So pressure work is 0 until total volume. Okay, this is V2. The amount of heat, okay, it is isothermal also, and ideal gas is present. So for isothermal process, internal energy is 0 for an ideal gas, because internal energy is a function of temperature. Sir, work 0, internal energy 0, then it is asking about Q, heat absorbed. Sir, it will also be 0. The question is unnecessarily tricking you by giving all these data of the volumes. You just apply FLOT, first law of thermodynamics, because what Sir's first law is, Q is equal to delta U is equal to Q plus W. This is 0, this is 0. Q will be 0. Moving ahead. Now, again, a similar question, the J2 2019, ideal gas undergoes isothermal compression. Okay, compression. Sir, you said we do not have to worry. Do not worry. This is V1, this is V2. Answer already have. So V1 is this, V2 is this. Against a constant pressure. Okay, pressure is constant. So again, you tell me what work? Sir, irreversible. Calculate irreversible work. Sir, minus P external into delta V. What is delta V for us? Final minus initial. I told you, you do not have to think about, sir, what is compression, expansion. You put final minus initial, formula will take into account your, whatever sign convention you will have will give you the answer. So this is minus 4 becomes plus 16. What is the unit? Newton meter square into, okay, it is Newton meter. Newton meter is SI unit only, so it will be joule only. So I am having plus 16 joule of work. Now, that means work is done on the system, because by the system will be negative. Now, heat released in this process is used to, okay. So this is work, and since it is isothermal process and ideal gas is taken, so delta U will be 0. Work we have calculated, so again applying the same thing, delta is equal to Q plus W. Some ideal gas is doing this first law, following first law. This is 0, Q becomes equal to W. We have calculated it is plus 16. So obviously some heat will be released. This much joule of heat is released by subjecting ideal gas to such a situation. So this ideal gas has released energy. Now the question is saying that this released energy, this 16 joule of released energy, because Q is negative. So the question is mathematically right also. Terminology wise, it is also right. Word problem. So this heat is used by to increase the temperature of 1 mole of aluminium. Now heat capacity question it is using. Let's say in a system I have aluminium. How much of aluminium? 1 mole. And I am supplying this Q heat, that is 16 joule of heat is given to aluminium, and heat capacity of aluminium is given. I told you for heat capacities question you should always look at the unit. So what heat capacity is given? It is given out to be 24. What is the unit? Joule per mole per Kelvin. Now see, they have, okay, over here they have written also molar heat capacity, though it's okay. Sometimes they hide. So you just tell me what will be the formula, sir? Sir, with unit also we can see, sir, it will be equal to Q upon N delta T. Finished. So what is the Q I am supplying? 16. So 16 upon what moles? 1. What is delta T? That we have to find. It is equal to heat capacity 24. Answer. What will be value of delta T? Delta T will be equal to 2 by 3. Will give you the answer. So this is how you do some heat specific heat capacities type of questions. Now next we are approaching work in an adiabatic process. So what's an adiabatic process? We already know it's a process when heat exchange is 0. So adiabatic process for us is when Q is 0. Now I have written some basics for you, not actually basics, but yes, a basics of your physics thermodynamics. So I'm not investing much of time in the derivation of these mathematical forms of adiabatic process. Why? Because for JEE mains, not at all they are important. For advance also, because physics you or anyway do this derivation. So I am just taking the outcome. So for an adiabatic process, what mathematical forms are followed? PV raised to the power gamma equals constant. T into V raised to the power gamma minus 1 equals constant. T raised to the power 1 minus gamma into temperature raised to the power gamma becomes constant. You can very well interconvert these three forms, the first form being the most important. Now, as already discussed, what was gamma, sir? Gamma is, I am now naming Poisson's ratio, ratio of Cp by Cv. We already know, what do we know? That Cp minus Cv equals R. I hope you remember this derivation, this conclusion from the previous slide. So if Cp minus Cv equals R, I just need one another formulation. So let's just try and convert it into gamma. Sir, how can we do that? Divide by gamma. So I can easily say Cp upon Cv minus, if Cv gets divided by Cv, it becomes 1 equals R upon Cv. So I guess you can clearly see this is gamma. So what I have is gamma minus 1 equals R upon Cv, or simply I can say Cv is written as R upon gamma minus 1. This is a very important point, and one more logic that you should know, that is calculation of Cp. We have already discussed the degree of freedom for any gases. Let us again repeat that formula. Delta U internal energy change for any ideal gas is equal to F by 2 RT. Obviously into number, this is for 1 mole of ideal gas. Sir, can you also tell me F by, okay, because this is changed, so F by 2 NR delta T, I'm sorry. Now, can you also relate this with the internal energy can be written as heat in form of heat capacity? It can be written as what? It can be written as NCV delta T. So you can clearly see what all things are same. So delta T same. Instead of, if I'm taking 1 mole, so this N will become 1. So can you clearly see in place of CV what I have? Yes. So you should definitely keep this conclusion in mind that CV is equal to F by 2 R. So what will be the value of F? Again, monatomic 3, diatomic 5, polyatomic 5 if it is linear, and polyatomic non-linear it is 6. So you can definitely calculate CV. How can you calculate CP? CP is equal to CV plus R. What is gamma? Ratio of CP by CV. There is another relation, CV is equal to, sir, why you are telling all this? These all are your physics facts, but I will be just using them for my chemistry questions. How? Just revising of physics facts and coming to a theoretical observation of adiabatic process. Like, these walls are adiabatic, as in no exchange of heat will take place. We know that. Now let us say the gas present inside is undergoing expansion. Sir, if gas will expand, gas will do work. It is not getting any heat from outside because we are discussing case of adiabatic process. So if I'll do work, I'll get tired. We discussed in the previous slide also. I'll get tired. So if I'll get tired, at what cost I have done this work from my internal energy? So if I move and expand, the temperature will fall and cooling of gas will take place. So when during an adiabatic process, if gas expands, cooling will take place, as in its temperature will fall. Let's say initially its temperature is T1, then whatever T2 it will gain will be lesser than T1 because temperature will decrease. Similarly, if we are compressing the gas, then the molecules will collide, kinetic energy will increase, and kinetic energy increasing as in temperature will increase because internal energy will increase. Internal energy of an ideal gas is a function of temperature. So if it is undergoing a compression, so heating of ideal gas will take place if undergoing a adiabatic compression. This also you have to, for theoretical questions also, and for sometimes we definitely see some questions that these logical developments will be very useful along with this. So in this slide, this is your conclusion. And along with this, after explaining adiabatic process, we can definitely calculate work done in adiabatic process. How, sir? Let's see. Now it is very easy for us. We know from first law, what do we know, sir? Again, we have to do that. Yes, that's why I said it's simple. Internal energy change is equal to heat given to the system plus work. Let's say, firstly, I'm calculating irreversible work. Okay, reversible work. Let's say I'm calculating reversible work first. Sir, adiabatic process, so Q will be 0. So I'm expanding or compressing reversibly and adiabatically. Sir, how can I calculate this work? Easy. This reversible work can be adiabatic because Q is 0. What is del U, sir? It is equal to NCV delta T. So this is one formula. Just like this, sir. Yes. Another form, recently we have derived CV, R upon gamma minus 1. So, or I can say this work reversible can also be calculated as N into R upon gamma minus 1 into delta T. I'm just writing delta T also, T2 minus T1, because to some people sometimes it becomes very new. Sir, they are not T2 minus delta T. Now, another form, some people say that because we can replace this temperatures also. How? Multiply this NR, so it will become NRT2, it will become NRT1. For an ideal gas, PV is equal to nRT. So another form, sometimes the question may not supply you with temperatures. It may supply you with pressure and volume. Then use it. How, sir? nRT is PV. So at time 2, at final state, so at 2 state will be equal to P2 V2, whatever it will be, higher, lower, final state is P2 V2 minus initial state is P1 V1. How you have written it, sir? nRT equals PV. So nRT of state 2 equals PV of state 2. nRT of state 1 equals PV of state 1 upon gamma minus 1. So these are three important formulas which sometimes mains will, sometimes this is not very probable, but sometimes mains can ask you these questions. Now, after defining this work, let us see some questions which will be helping us to understand this more. Now, let's try this question asked in 2019 mains. Although not asking exactly work, but conclusion of those adiabatic which we have just seen will be definitely employed. So we can see how J asks. The question says 5 moles of an ideal gas, you are given moles of gas. Again, it's an ideal gas and at 100 Kelvin. So this is T1. Are allowed to undergo reversible compression till its temperature becomes 200 Kelvin. As in temperature is getting increased. Sir, temperature is getting increased. That means it is getting heated. Yes. Sir, during compression it is getting heated. If I'm compressing the gas, how come it is getting heated up? Remember, if we are compressing the gas, how come it is getting heated up? So these are certain things which, I mean, you just look at the question. It is nowhere mentioned it is adiabatic. So that's why some theoretical details are sometimes theoretically asked and sometimes are hidden in the word problem. So sir, because the question is saying it is getting heated up, that means it is taking an adiabatic process. So Q is 0 for such a process. Because we are asked delta U, so first let us find float, which is first law. Q delta U is equal to Q, which is 0. Now we know, plus W. What will be W? Sir, W will be equal to of the adiabatic process. We calculated W also. NCV delta T or this. Sir, we are given temperature, so let us use this. Are we told what type of gas we have? We have an ideal gas and no, its degree of freedom is not actually told by the question. It is just asking you the value of delta U. Sir, but delta U we can calculate using work. But since we are not told about the type of gas, so what F I can take? So instead of that, can't you think of another formula? What is it? Sir, we know delta U is equal to NCV delta T. Remember? And I guess for the gas, the value of CV is directly given, although it is not given what type of gas it is. If it would have been given, we can calculate the value of F. It is directly giving you value of CV. So delta U is equal to, from heat capacity, we know it is equal to NCV delta T. So you do not have to actually calculate work. Put the value because you have to calculate delta U only. That will definitely be equal to work reversible. So how many moles, sir? Sir, moles is 5. What is value of CV, sir? Value of CV is 28. Remember, it is in joule. Answer is in kilojoule. Mark this thing. After this, what is delta T, sir? We do not have to worry. Final minus initial is our thing. What is final? 200 minus 100 is 100 Kelvin. Do the math. I guess this is quite easy also. 40. This is okay. Answer is in kilojoule. So firstly, divided by 1000 also. So it will come in kilojoule. So this 0 gone. This is 2. This is quite easy also. That's why I'm helping you to do it. 14. That means answer is not A, it can be BCD. What about, then you have to calculate delta PV. Sir, how we calculate delta PV? See, change of pressure volume you have to calculate. Mind you, the question is not telling pressure constant or volume constant. Then do the basic like we have done for the general case of delta H. What is change of PV? Sir, P2V2 minus P1V1. This we have to find. How can we find P2V2? This value we can find. How can we find P2V2 minus P1? Sir, for gas, PV equal to nRT. So at state 2, what will be P2V2? It will be equal to NPV equal to nRT. So it will be nRT2. Moles are fixed. R is fixed. So P2V2 at state 2 will be equal to nRT at state 2. Minus P1V1 nRT1 at state 2. This is what, although work is not asked, but see, this is what I told you when we were converting this T2V2 into this. So all the logics, all the basics that we see can be used directly in mains. So now you can easily solve. So it is nothing but it is NR Instead of CV, I have to put R. What is the value of R? R value is also given. It is 8. So NR delta T. What is N? 5 moles. What is R? 8. What is delta T? 100. So it is also easy. Divided by 1000. So this is 8 5 ja 40. 40 by 0. This is 4. So your answer is yes, 4. Your answer is C. So just let's check the calculation and we move forward. So let us apply what we have studied in this question, although it's an advanced question and in fact has been asked 2 times, 2005 and 15. But a very basic if you just follow your confidence. 1 mole of a monatomic gas, the gas given is a monatomic gas, expands adiabatically, so definitely Q is 0. From initial temperature to a final temperature, and the final temperature you have to calculate in this form. It is adiabatically, it is subjected to external pressure that is constant, that is work is, sir, work is irreversible. So you tell me Q is 0. First law, applying first law, you can easily say delta U is equal to Q is 0. So it is W. But what? W irreversible. Sir, whatever formula you have derived, it is for reversible process. Don't you worry. Just apply the basic. What was an irreversible case? Sir, minus P external into delta V. Do that. What is the external pressure, sir? Minus of 1 atm. What is delta V? V2 is 2 liters, V1 is 1 liter. So this is 2 minus 1 because for us, change is always final minus initial. What formula I can use over here, sir? NCV delta T. But if you just check the options, in all the options 2 by 3, 3 by 2, okay. Over here, not 2 by 3, 3 by 2 is not there, but 5 by 3. So what does it tricks you? It tricks you of thinking a formula where some ratio can come up. So can you think of the formula of any form of CV which can be expressed as a ratio? Yes. Poisson's ratio is gamma. Can you tell me what is gamma for any gas? Sir, it is ratio of Cp by Cv. Can you tell me what is Cv for a monoatomic gas? Sir, it is equal to 5. Sorry, for monoatomic gas, it is 3. So it is equal to 3 by 2R. Can you tell me what is the value of Cp? So Cp is Cv plus R. That is 3 by 2R, 3 by 2R plus R. So can you just find the ratio? Sir, it is simple. It is 5 by 3. Please do check, everybody. Now you have the value of gamma. So this 5 by 3, this 5 by 3 factor is somewhat visible to you, sir. But how can I use gamma? Remember, Cv is equal to, we have derived Cv in form of gamma. What was that? Cv can also be written as R upon gamma minus 1 using that. So this is number of moles is N into R upon gamma minus 1, as in 5 by 3 minus 1 will come to the denominator, into what is delta T, final temperature, let's say T2 minus initial temperature. You have to take that initial temperature as T. It is simple, sir. The appearance is although not that simple. It is equal to minus 1. Moving ahead, what else you have, sir? Nothing. I guess it is quite evident now. What you have to calculate this final temperature. Let's say we use this minus 1 over here. So this T2 minus T becomes T minus T2. Put everything over there. So this 5 by 3 minus 2 is 2 by 3. Going over there becomes 2 by 3. This R will be coming to the denominator. Answer, sir. We have to find T2. So what is T2? T minus 2 by 3R. And I guess R you have to put as 0.0821. Look at the options. T minus 2 by 3R. So this is your answer. Is it that difficult? No, sir. We just have to follow the basic. Moving ahead. Now, sir, we have already covered this. Let us revise it again. whenever gas is undergoing expansion, amount of reversible work magnitude is much higher than the irreversible work already seen. Similarly, when gas is undergoing compression, amount of irreversible work magnitude was higher, which we can already see through graph. What was the logic behind it? Whenever we are starting irreversibly, cut with a slight fraction of second, the pressure already reaches to the final pressure, and then volume either decreases or increases. So therefore, area under this curve will be irreversible work. Area under the whole curve will be irreversible work. So obviously, irreversible work in compression is higher and reversible work in case of expansion is higher. We already know this, sir. Why telling again? Because now I am dealing with temperature. I told you this expansion and compression can be any. It can be isothermal, it can be adiabatic. But recently we have digged into adiabatic. So let's say if it is isothermal, taking first case first, isothermal. Sir, if it is isothermal, whatever be the initial temperature, that will be the final temperature because it is isothermal. So isothermal, there is no temperature comparison because temperature remains same. But if you are taking an ideal gas reversibly and irreversibly, taking what? You are expanding an ideal gas, both reversibly also and irreversibly also, but adiabatic reversible process and adiabatic irreversible process. One thing we definitely know till now, sir, if you are expanding a gas adiabatically, gas will work because no one is supplying heat to the gas, so gas will get cooled, remember? So obviously the final temperature, let's say the final temperature is T2. Yeah, let's say final temperature is T final. This T final is definitely because the gas has cooled down during expansion. So the T final will be obviously lesser than T initial because gas has cooled down. What I'm asking is T final reversible and T final when adiabatically expanding irreversibly. Among these two, if the process has been taking place adiabatically, now you compare them. Sir, it is also very easy. In which case you have done more work? Reversible. Reversibly, sir, if more work is done by the gas must have cooled down more. So reversibly, if gas has cooled down more, its temperature would have been much decreased than the irreversible case. Very important. Logical, not important as per mains, but very logically important. Now, again, sir, isothermally, if we are reversibly or irreversibly compressing, temperature will be same. But if I am doing it adiabatically, then this thing I know, sir, you have already told us, during compression, final temperature gas will be subjected to heating. Gas will be heated up. So final temperature over here will be higher than the initial temperature. Because here it was cooling, but here it was heating. So this final is definitely higher from its initial temperature. But what I want to compare is, what can you say about the final temperature when done reversibly and final temperature when done, irreversibly? When done irreversibly. Irreversibly. Can you give me this picture? Yes. Sir, which case work is higher? Over this case. So gas has been worked upon because we are compressing. So we are working on the gas. I am working on the gas to a larger extent, irreversibly. So it will be heated to a larger extent. So its final temperature will be more. So irreversibly, the final temperature reached will be more than the reversible one. So you just check. In both the cases, reversibly final temperature reached is lesser. Now, this is a very important and a very common logic. Now this is also a question for us, a very logical question. See, there are three gases ABC. The gases also I have given: helium, oxygen, sulfur trioxide. They are undergoing adiabatic expansion. Now we know adiabatic expansion as in volume is increasing. Adiabatic as in there will be a curve. But what graph, what mathematical function it will be following? Although its trend is similar to that of an isothermal curve, but this is adiabatic curve because question is telling us. So they are also a curve. The relation is PV gamma is equal to constant. So we can very well see this gamma will decide the slope of the curve. So I'm just simply writing that gamma decides the slope of adiabatic curve. So you tell me which slope is higher. Sir, all the gases are starting from an initial point 1. They are expanding and reaching to a final volume, but pressure from the similar point, pressure of gas C is much reduced, as in the slope with which C gas has traveled is larger. So from here we can definitely see C has a larger slope, large gamma. A has smallest gamma, and B should have intermediate gamma. So I just have to calculate gamma for ABC, and I do not know who are ABC. These are 3 gases and I have to designate which is A, which is B and which is C. So whoever gas has the highest gamma will have the highest slope. And who has the highest gamma? Let us check. So can you tell me the value of gamma first for a monoatomic gas? Yes, for monoatomic gas, just we have recently done, it is 5/3, remember? So for diatomic, it will be F is 5, so 5 plus 2 is 7, so it will be 7/5. And for triatomic, that to non-linear, degree of freedom F is 6. So 6 plus 6/2 is 3. 3 plus 1 is 4 upon okay, I'm calculating it for triatomic. See, CV is F by 2. F by 2 R. F is 6. 6 by 2 R is 3R. What is CP? What is CP? CV plus R. So 3R plus R is 4R. Now I hope you should remember also value of gamma for monatomic, diatomic and polyatomic. This is polyatomic non-linear. So if you just calculate this value, I guess this will come out to be 1.67. 7/5 is 1.4, I guess. And this is definitely 1.33. Sir, monoatomic has highest gamma. And as the atomicity is increasing, gamma is reducing. So you can predict the atomicity of gases by comparing the curve. So can you tell me which has larger gamma? C. So C will be helium. So this gas will be, your C gas will be helium, your B gas will be oxygen, and your A gas will be SO3, because the gas which has higher gamma, its atomicity is lesser. Now, one more comparison. Now over here also, you know what is isothermal? PV is equal to constant. What is adiabatic mathematical equation? PV raised to the power gamma becomes constant. Now I'm trying to just make it short. I'm giving you a trick to remember this. Whenever you are supposed to compare, because trend of both isothermal and adiabatic PV curve is same. So whenever you are supposed to say that which curve is the isothermal curve and which is the adiabatic curve, just do one thing. Put the thumb on the starting point, like it is case of expansion. So both are starting from this point. So put the thumb on starting point and move your fingers. Whatever graph you encounter first will be isothermal. So when I am putting the finger at the initial stage and pointing my fingers, curling them down to clockwise direction, the graph I'm meeting first is the yellow one, and therefore I'm saying this represents the isothermal process, and the green one represents the adiabatic process. Simply. Obviously, this is not a rocket science. You can very well derive also that this pressure reached, this one, this pressure reached will be isothermal pressure, and this pressure reached will be adiabatic pressure through the PV is equal to constant is used for isothermal, PV raised to the power gamma is used for adiabatic. Gamma is always more than 1. That it is not rocket science. You can very well derive that also, that this will be isothermal and this will be adiabatic. You just give me an observation and tell me area under which curve is higher in case of expansion? Isothermal. So which work will be higher? Isothermal work will be higher than adiabatic work during expansion. Now, during compression, do the same thing. From where we are starting if we are compressing? Starting from a volume, and then volume is getting reduced. So what I've told you, put a finger. Your finger should go into clockwise direction. The graph you meet first will be your isothermal graph, and obviously the graph that will be followed by the first one, if first is this and second is this. So during compression, area under which curve is higher? Adiabatic. So during compression, which work is higher? Adiabatic work is higher than isothermal work. This is also a very important conclusion. Just put the finger in the start, curl your finger clockwise. Whatever graph you attains first is the isothermal graph. Moving ahead. So let us now quickly move into the calculation of work done in cyclic processes. What are cyclic processes? Whenever a system starts from a point and returns to the same point. So how can we calculate work? We already know, sir, PV graph is given, then area enclosed by PV graph will give you work. So for a cyclic process, the area enclosed by the cycle will give you PV work. Like over here, this is a rectangle. What is the length enclosed by the rectangle? Sir, for the cyclic process, I have to calculate the enclosed area, not this below area, because this process is getting reversed. I mean, it is a cyclic process. So for a cyclic process, the enclosed area has to be taken. So only this much value I have to take. So you can very well find out the area of the rectangle. Sir, 2p minus p. So this is P and this is V. So what is the area? PV. But if you try and calculate it mathematically, logically, what can you say? Sir, for that we have to go to each step. So let us first go to each step. So what can you tell me about work from A to B? Sir, A to B is a pressure constant case, and because expansion, so it is nothing but isobaric expansion. Okay. Because pressure is constant, so what work it is? Sir, irreversible. What is the formula of irreversible work? Minus P external into delta V. Easy, sir. What is external pressure? 2P. So minus 2P times of what is delta V? Final volume is at B, which is 2V minus V. So this is V. Easy. This is minus 2PV. Can you tell me what is the work done from B to C? First, you tell me, sir, what is B to C process? Sir, volume constant. So if volume constant, then obviously work is 0 because it will be an isobaric process. Remember? Now, from C to D. Okay, sir. Work from C to D. Sir, it is exactly opposite. Yes. So this is isobaric, obviously because pressure is constant. But what? Compression. So this is isobaric compression. You do not have to name. I'm just giving the basic in one and will be generalizing. I'll be giving you a trick. So first, let us understand through the basic. Okay, sir. What is the constant pressure? P. What is delta V? V final. For C to D, D is the final volume. So V minus 2V will give you minus V. So this is plus PV. Again, can you tell me work from D to A? Sir, again isochoric, sir. So same. Gone. Now you tell me what is the total work? Add the 4 steps. This plus this plus this plus this. 0, 0 will not contribute. Minus 2V plus 2V, your answer will be minus PV. Sir, if total work is minus PV, you said area under curve, which was PV. But this is minus PV, that means this is work done by the system. Statistically, we have done these questions. Obviously, we as in thermodynamic scientists have done this. And now we have come up with a trick, with a final conclusion, mathematical observation. Not to trick, word not to be used. It's a mathematical justification, observational thing. What is the observational thing? Sir, whenever we are supplied with PV curve, as in P is in y-axis, P is in y-axis, volume is in x-axis. Remember this thing, P has to be in y-axis. In those cases, if the cycle is clockwise, then work done is negative. And if the cycle is anti-clockwise, work done is positive. You have to remember this. Make a trick to learn this, but you should learn this. Now, obviously, if the graph changes as in y becomes your y-axis gets the volume term and x-axis gets the pressure term. In that case, opposite. Then clockwise will give you positive work because over clockwise was giving you negative work. So what about that question? Sir, this is a cyclic process. A cyclic process with a clockwise cycle with P in the y-axis. So work will be negative. Moving ahead, sir, are these questions asked? See for yourself. JEE Mains 2024, every year they are very, they are in love with this. Area enclosed is this area because it's a cyclic process starting from A, ending to A. Can you tell me, now I will not do the step-by-step basic. Why I should? I have invested my time in explaining. I will directly calculate area under curve. What is area of a triangle, sir? Half of base. What is base? Sir, this thing. What is this thing? This is pressure. So what is pressure? 30 minus 10 is 20. But it is kilopascal. What is SI unit of Pascal? Sir, sorry, what is SI unit of pressure? Pascal. So kilo, 10 is power 3 added. Pascal, I am happy because it's an SI unit of pressure. And P into V through MLT system, I know it's nothing but Joule. So no conversion also will be required. So pressure in Pascal and volume, what is SI unit of length? Meter. So volume meter cube. Oh, sir, it is given decimeter cube. No problem. 1 decimeter is equal to how many meter? 10 is power minus 1 meter. So 1 decimeter cube will be equal to cube of this. Therefore, cube of this minus 3 meter cube. These mathematical conversions through physics, through mole concept also we discussed. So you should remember. Now, what is this length of AB? So 30 minus 10. As in again, okay, this is also 20. But because it is decimeter cube, so in order to convert into meter cube, I'll be giving a 10 to the power minus 3 multiplier. So meter cube and this is Pascal. Sir, all is SI unit, so need not worry about unit. It will directly through MLT system, you know through physics, it will directly be Joule because pressure is in SI unit, volume is in, length is in SI unit. So no conversion also required. Solve it, answer. So I guess this is quite easy. This is gone. This is 200 and 200. Sir, but what about plus minus? What graph it is? Volume on y-axis. Volume on y-axis. So clockwise will give you positive work. Hence positive work, that is work done is on the system. Work is positive. That these questions come? Yes, 24. Now 1 year later, 1 year before, 23. Similar question. Answer I have already given, but let us check also. From 1 to, okay, I'm starting from 1, reaching to 1. Okay, sir, it's a cyclic process. So can you calculate work from 1 to 2? 1 to 2 is, I have written 1 to. Sir, again, it's a isobaric process. So what is formula? Minus P external into delta V. What is minus P external? Sir, 1, okay, but pressure is in bar. So minus 1 bar. Oh, this is not SI unit. Now conversion will be required. What is volume? Unit? Okay, I'm sorry. This is volume and given in liters. I'm just giving you this. This was a misprint. I'm telling you this is volume in liter. Was given in the question. Okay. So volume in liter. What is final volume? 40. What is initial volume? 20. Because 1 to 2, 2 is the final. So 40 minus 20. 40 minus 20 is plus 20. But unit will be liter. Okay. Now, sir, this is bar liter. We have, although I've told you there also, but I have not written that because question was not saying that. 1 atm liter is equal to how many joule? 101.3 joule. Now, 1 bar liter is actually much simpler. It is 100 joule. So just use a multiplier 100. So this bar liter will give you minus 20 into 100, that's it, 2000 joule. So I have calculated this work from 1 to 2. Sir, why not calculating the area? Because through the basic mathematics of class 10th we have, this is not a well-defined figure for us. It is not even a triangle, it is not even a square, it is not even a rectangle. So its area is not defined. So I'm, instead of doing mathematics, I'm doing my basic mathematics of thermodynamics. So I've calculated work from work is a path function. So total work is 1, 2 plus 2, 3. Oh, sir, 2, 3 you do not have to calculate. Balle balle. Why? 2, 3 volume constant. Volume constant, work is 0. Bingo. So what is left, sir? Okay, sir. 3 to 1 is only left. But, sir, 3 to 1 is what type of process? How do we know? This is isobaric, this is isochoric. What about this? Curve is isothermal also. Curve is adiabatic also. What is this process? Now, in order to check, I am giving you a final verdict. Adiabatic mathematical formula is PV raised to the power gamma equals constant. This is monatomic given also, so it may be adiabatic. But if it is isothermal, then definitely temperature will be constant, so PV will be constant. Because isothermal equation is PV is constant, adiabatic is PV raised to the power gamma is constant. Gamma, putting gamma and calculating is difficult. So if it is isothermal, the product PV will be constant. And if it is not isothermal and given a curve, then it will be an adiabatic process. So what technically you should do is check for being isothermal or not. And that is easy to do, because if a process is isothermal, temperature is constant. If temperature constant, product PV is constant. So at point 3, can you tell me what is the product of P3V3, as in pressure at point 3, volume at point 3? Do not convert, because we will use that unit also over here also. So calculate P1V1 and calculate P3V3. If it is an isothermal process, the product will be equal. If not, it will be an adiabatic. So we will use adiabatic formula for work. P3V3, pressure at point 3, okay, volume is 40 and pressure is 0.5. So this is 40 into 0.5 is 20, okay. P1V1, pressure, volume is 20, pressure is, it is also 20. Arey, sir, it is isothermal. If not, it would have been adiabatic. If not, it would have been, you can check also, because gamma for monatomic is 5/3. But sir, checking adiabatic we will be required to do P into V raised to the power. That will be more mathematics. Why do more mathematics? Check isothermal. If not isothermal, it will be adiabatic, because both are curved, and here it is isothermal. So thank God we are escaped. Now use the formula. What formula you will use while calculating work? For in the case of reversible, we were assuming isothermal, and then we have reached to the formula. What formula? Minus 2.303. Okay, in the question ln is given, so I'm not changing it to log. I'm using natural log. So it is minus nRT ln of V2 by V1. You do not have to worry about expansion, contraction. V2 is final, V1 is initial, whatever it is. Because I am calculating from 3 to 1, so reaching 1 is our final destination. What is number of moles? Sir, 1. What is R? In such questions, data are also given. So check for the datas first. Okay, R value is not given, sir. But since we are calculating work, so 8.314 into. What is constant temperature? Must be given, because it is an isothermal process. Are we supplied with constant temperature? No. But you can calculate that constant temperature. How? I'm just telling you. But let us first put the values. What is ln? ln of V2. What is V2? Sir, final volume is, because I'm going from 3 to 1. So final volume is 20 and initial volume is 40. See, final upon initial. This is log 1 by 2. Okay, log 2. So ln value, actually point is, because they have given ln 10 is 2.3, that means they want ln 10 is 2.3 into log 10. Log 10 we very well know 1. So instead of 2.303, the question is asking you to take 2.3. So how am I modifying this formula? I'm not using actually this one. Why? because the question wants me to convert it into log, because this ln10 is given. So I'm using the formula minus 2.303 nRT log of V2 by V1. This one I'm using. So minus mole is 1, R is 8.3, temperature, I'm just helping you with it, into 2.303. Instead of this, I'm writing 2.3. Why? Because question is telling me to do that. So at least some of your calculations will become easy. Into log of V2 is 20 by V1 is 40. So I'm directly writing 1 by 2. So what is log of 1 by 2? 2 raised to the minus 1. So minus 1 will be coming over here. So answer will be becoming positive. So it is 8.3 into 2.3 into what is log 2? Log 2 is 0.3. Now what is left is I have to calculate this constant temperature. How can we calculate this constant temperature? Apply PV equal to nRT. How, sir? Apply PV equal to nRT at any state because temperature is constant at any state. Let us apply it at state 3 only. So what is pressure at state 3? Pressure at state 3 is 1.2 bar. Volume at state 3 is 40. Number of moles is 1. R is 0.083 in terms of bar. Into temperature. Sir, this we have to calculate because temperature is same here also. So calculate from any side. Sir, this is easy. This is 10. So what is your answer? 0.083. This T is 10 upon 0.083. Okay, this will help you in calculation also because T you have recently calculated as 10 upon 0.083 and this is 8.3 because 8.314 I'm writing as 8.3, the value of R, because if it is R only, no. So this R, but here R I have to use for bar and liters, and here this is 8.314 because I am using for joule because work has to be calculated in joule. But luckily those values are approximately, you can see they are same. So if I move these two decimals by 2 places, I'll get 2 zeros over here. So this is 8.3 and this is 8.3. It will get cancelled. See, the mains question is helping you in calculations also. So this we have separately calculated T and used T over here, which cancelled these two factors. So what are we left with? 2.3 into the 3 is 9, 3 is 6, and then there will be 2 decimal. So this is 0.69 into 1000. So this is nothing but 690 joule. Okay, sir. This is 690 joule with a positive value because this minus was log of 2 raised to power minus 1 as converted. The calculation you have to do sometimes. So this is 690 and this is minus 2000. So do the math. 2000 minus 690. What will be your total work? W12 plus W230 plus W31. W31, we just do the calculation, just do the plus minus. Whether I'm getting that answer. Answer is okay, 620. Just check whether we are right in calculations. Yes, guys. Just check over here. We have to be precise with calculations. This is 40 by 2. So this will actually be 20. So this is actually temperature is 20. So over here, this will be 20 and giving 2 zeros will make it 2000. So a factor of 2 will be included. So a factor of 2 will be included. So this will be 1380. So if 2000 is minus 2000 when added with 1380, it will give you 620. So in that case, you will get your answer. Or else what we would have done easily also, that this is a factor of nRT, temperature is not given, but we know for gas, ideal gas PV equal to nRT. So instead of this nRT, we could have directly used this product PV, which will be 20, but this 20 would be in bar and liters. So in order to convert this 20 from bar and liter, we would have definitely multiplied this 100. So it would have directly given us 2000. What we have calculated by other way around. The point is sometimes calculations you have to do, and do these calculations very religiously and very neatly. Because over here, because our neat and cleanness was disturbing, so were missing. I was actually missing that this is 40, so it will be 20, not 10. Moving ahead. So calculations will come with practice. Sir, this delta H and delta U, how can we calculate? This is provided to you. Sir, if it is provided to you, it must be getting calculated experimentally. Yes. How do we do it? The apparatus in which experimental determination of delta H and delta U happens are called calorimeter. And now we very well know if heat is exchanging between system and surrounding at constant volume, then whatever heat exchanged will give you the value of delta U, because heat exchange between system and surrounding at constant volume is nothing but value of delta H, and heat exchanged between system and surrounding at constant pressure will give the value of at constant volume will give you the value of delta U, and at constant pressure will give you the value of delta H, which is enthalpy change. Now, how it is done? Just I'm giving you a basic. Let us say there is a chamber with oxygen under pressure, and let's say I'm some molecule is undergoing combustion. If a combustion of any, let's say methane, is getting combusted in this chamber, after combustion, what the result will be there, sir? Heat will be produced, because exothermal is because combustion is an exothermic process. What that heat will do, sir? That heat will rise temperature. So temperature of this water will rise. Let's say this is thermometer. Let's say I have a digital thermometer. Let's say the initial temperature was T1 and it rose to value T2. What is the difference of temperature? Delta T. So for delta T temperature rise, if you know the heat capacity of the system, so remember, and I know how much moles of the compound I am subjecting to combustion. So number of moles into heat capacity into delta T will give you what? Sir, will give you amount of heat. Q is equal to NC delta T. Sir, but it was CV or CP. So do it at constant volume. So it will be CV. And you will be getting QV. Sir, what about these heat capacities? Heat capacities of the calorimeter, as in for the setup that you are using, is already given in the data sheet, because you must have bought this calorimeter from somewhere. So the data sheet of the calorimeter will be telling you that what is its heat capacity. Now, knowing this is more and more than sufficient for means. So when done under constant volume, that particular calorimeter is known as bomb calorimeter. Now, this is very important. When heat exchange between system and surrounding is observed in a calorimeter, and what calorimeter? A bomb calorimeter. That means you are undergoing that process under constant volume. So what volume, what heat exchange you are getting? QV. So what value of thermodynamic variable you are getting? Sir, delta U. This you have to learn. So bomb calorimeter is constant volume apparatus, so it will give you value of delta U, while a simple calorimeter, when it is not mentioned, this is also a calorimeter, but here through some physical constraints, we are keeping the pressure constant. So here system surrounding will be exchange heat under constant pressure. So it will give you the value of QP. That means it will give you a value of delta H. This is the basic that you should know, sir. If we know this basic, we will do question. Yes, because heat capacities we have already spent too much of time on. Now this is a question, a mains question. Answer also I've given. A reaction is given. Obviously, the combustion is going on. Reaction is balanced also. The amount of heat produced as bomb calorimeter. Bomb calorimeter is producing heat, as in it is QV, as in this is value of delta U is the point. That's it. So delta U given, sir. Temperature given, sir, 300 degrees Celsius. 300 Kelvin, I'm sorry. And you have to calculate enthalpy of combustion. Enthalpy of combustion as in delta H you have to calculate, which is given out to be minus X. Remember, unit is in kilojoule, so kilo factor. So just calculate this value. Obviously, it will be coming out to be negative. The minus and that value, magnitude, will be your answer. So delta H, what is the formula, sir? Delta H for a reaction is equal to delta U plus delta NGRT. Now, I'm again leaving the most difficult part for you, which is into divide. Because when we are subjected to a very short class, we cannot be relaxed and do introduct. You can do relaxed introduct when practicing at home and when doing JEE. Now, what is delta U, sir? It is 726 positive only. So kilojoule, so no tension. What is delta Ng for the reaction? For only gases. So delta Ng is this 1, 2, because this is liquid, so I'm not bothering. This is also I'm not bothering. So 1 minus 3 by 2 is your delta Ng. As in 3 by 2 is 1.5. So this is minus 0.5. So what is delta Ng? Minus 0.5 into what is the value of R? R is given 8.3. What is temperature? 300. But if R is used as 8.3, it is joule. So in order to convert to kilojoule, I'm dividing by 1000. Now you have to do the math. Obviously, you will get an answer. I've given you answer also. So 226 will be, some value will be getting subtracted. So what are you are getting? I have mentioned, okay, you have to, I guess this value will be so small that if you round off to the nearest integer, it will be 727. Okay, if something is getting subtracted from 726, how come you can get 727? Delta H is equal to delta U plus delta NGRT. Delta Ng is coming out to be negative. The reaction is balanced. Let us check. Reaction is balanced. So 1 minus 3 by 2 will give you minus. So this will be lesser. I will just check here the answer for you, because over there the answer is written as 726. Let me check the answer for you. Okay, one more correction, as in not correction, word problem. Amount of heat produced as measured. So it is produced. This heat is getting released. Bomb calorimeter, so it is at constant volume. But if heat is getting released, then Q will be a negative value. So this value will be minus of 726, and obviously it will be also, so minus will give you ultimately a negative value, and the X that you will be getting your, now this calculation part is, I guess it will be very easy, but this theoretical thing that we have missed is the question is asking us that heat is produced, and if it is produced, then this has to be a negative value. Moving ahead. Now, this is a similar question. You just try this question. I have mentioned the answer also over there. Just the same question. Please try. So, this is nothing but the similar question. Like over here, this value, sir, this is also bomb calorimeter. So, if it is bomb calorimeter, what value you are supplied with, sir? Heat exchange between system and surrounding at constant volume. So this is delta U. Delta U value is again given over there. It was not given minus. It was saying that it is released, but we missed it over here. But you should keep that thing in mind. So delta U given, sir. Reaction given. So what is delta Ng? Can you tell me delta Ng for this reaction? Yes, this is 1. This is 1 because this is Balin reaction. So this is 2 minus. For reactant, this is solid, so not accounted. So this is 3 by 2, that as in 1.5. So this is 0.5. So delta U, do you know? Delta Ng, you know. R value, you know. What is temperature? Temperature is 298 Kelvin. So you just have to do the math, and the answer also I've given it 741. See, similar question all the time asked. So obviously religiously do these formulas. Now, just let us quickly move forward to the main area where maximum questions are asked related to delta H. So this is thermochemistry. Initially, till now, what we have done is thermodynamics. Thermodynamics is actually valid for physics side of thermodynamics. For chemistry, from here, this becomes the most important part. Thermochemistry is generally asked out of us in chemistry from thermodynamics. But yes, thermodynamics questions are also there, the first law questions, but main thing is thermochemistry. So let us move into thermochemistry. Now, what is thermochemistry? Sir, nothing. The value we know. What value we know? Heat exchange. What heat exchange we know from foundation classes 9, 10. Then enthalpy change. If reaction releases energy, we know it is an exothermic process. Delta H is negative. If reaction is endothermic, it will gain heat, so delta H of the reaction will become positive. But now I am using a proper word and calling it enthalpy of reaction, and hence writing this small r in the subscript. Now, One more thing you should know is whenever a chemical reaction takes place, the chemical reaction always proceeds by reactant collide and they reach a level of excitation. That energy is called activation energy. All reactants cannot form product. Only those reactants can form product who has the capability to form an intermediate which has the capacity to climb up the activation energy barrier. And whoever intermediates, when reactant collide, they forms an intermediate before formation of product, although it's the formation is for fraction of microseconds. But only those intermediates who has the capacity to cross that energy barrier called the activation energy, only those intermediates are able to produce products. We will do this in detail also when we will discuss chemical kinetics, but I guess this is a basic which you should all know. So, sir, if reaction is endothermic, then what does endothermic? Sir, change is always final minus initial. So if delta H for endothermic is positive, then I can say this is summation of enthalpy of reactants, and this is, let's say, supposing this is the summation of enthalpy of products. Final is product minus initial. If the magnitude of enthalpy of product will be higher, then only final minus initial will be a positive value. Similarly, if delta H is negative, that means summation of enthalpy of reactant has a higher magnitude, while summation of enthalpy of product has a lesser magnitude. Why? Because final minus initial, if minus is larger in magnitude, then only it will become delta negative. So one thing. Other thing what I told you is a reaction always proceeds how? Reactant first produces an intermediate which clear this energy barrier. And this energy barrier, my friends, this energy barrier this energy barrier is called the activation energy barrier. So all reactants who has the capacity to form an intermediate who can cross this barrier, they can only form product. Again, in chemical kinetics we'll do this, but since this is a very conceptual basic, so I'm telling you here also. Let's say this is progress of a reaction, rate of reaction. Let's say time required for progress of reaction is 10 seconds, for example. The maximum time, let's say 8 seconds, the reactant molecule will take to make their intermediate climb this activation energy barrier, and after this the product formation is in a jiffy. So this is always the slow step, and this is always the slow step, while this is always the fast step. So similarly over there, reactants will first form an intermediate who will cross the energy barrier, and this difference will be termed as activation energy. Now, sir, is it that important for us over here? No, it will be important for you in chemical reaction, in chemical kinetics. But this is a very important basic, hence I'm discussing and investing some few minutes in it. Now, moving ahead. Now, sir, now we know enthalpy of a reaction is nothing but heat of reaction, written as delta H of a reaction. Delta H of a reaction is what? Sir, remember, enthalpy is an extensive quantity, as in it depends upon the amount, and change is always final minus initial. So for a reaction, what is final? The products. The enthalpy of summation of enthalpy of products minus reactants. So what you have written, nu I Hi, as in this small c. What is enthalpy of products? Sir, enthalpy of C into small c, because how many moles of C are made? Small c. So because enthalpy is an extensive quantity, so you have to always balance the reaction, use their coefficients, and then write this reaction. But sir, you said absolute value is almost impossible, almost very difficult, although with a lot of hardships you can calculate absolute value, but technically, sir, absolute value we cannot determine. So sir, that's why now thermodynamics introduce various types of enthalpy of reactions, because this is the basic of enthalpy of reaction. But these enthalpies of reactants and products, their absolute value is not at all required. How? If we can define some various types of enthalpies. And that is actually the main chapter of thermodynamics for you, which is thermochemistry. So we are defining types of enthalpies of reaction. The very first type of enthalpy of reaction is standard enthalpy of reaction. Now, what is standard enthalpy of reaction? Standard enthalpy of reaction is just, this name is important, standard. See, like for gaseous, there is a standard temperature and pressure. Similarly, standard state or reference state for any element, for every element is individualistic for them. For example, I'll just give you some examples. For example, generally, although the temperature is also variable for all the elements that exist in nature, but in general, the question which is supplied to us, so whatever standard states, some standard states I'm giving you, and that will be more than sufficient for you in the paper. So generally we take standard temperature as room temperature. So standard temperature for us is generally 25 degrees Celsius. And what are the elements whose standard state we should remember? Some gases like hydrogen is H2 gas, oxygen is O2 gas, nitrogen is N2 gas. These are their standard states in which these elements exist in nature. So how hydrogen exists as S2 molecule? What state of H2 molecule exists as reference state, standard state, native state, as in nature allows them to form in that state freely. They do not require any energy to be existing in that form. So that is their native state, their most stable state. So for the gases, there are some examples. Metals generally exist as monoatomic atoms, and in what state? Solid state. So for some metals, carbon, although not a metal, but I'm giving you this fact, carbon solid. What solid allotropic form? Graphite, not diamond. Graphite is the most stable allotropic form of carbon, and hence graphite carbon solid is its reference state. Bromine is a non-metal existing as a Br2 molecule, but in liquid state is reference state. Iodine, I2 is a solid. Cl2 is a gas. Mercury, although a metal, but exists in liquid state at room temperature, so this is its reference state. Phosphorus, P4 molecule as a solid, but what allotropic form of phosphorus? White phosphorus. Similarly, rhombic sulfur, S8 molecule is its reference state. These some reference states I'm mentioning you should remember. Now, sir, again, go to this definition. What is enthalpy of reaction? When this not is represented, it represents a standard state. So, standard state of a substance, I have written these most stable state. At a specified temperature, generally the specified temperature for us is 25 degrees Celsius, although if you will grab my neck, for every element, the reference temperature is also different. For the sake of simplicity in questions, that is not asked out of you. In mains, in advance also, the reference generally, more 90% of the time, they take a reference as 25 degrees. If sir, they will change, they will specify. Mains will not do that, higher questions will do that. Now, isn't it pure form? And what is the standard pressure? 1 bar. And what are their pure forms? Their pure forms are different for different elements. Now, moving ahead. So first thing is, we will be more discussing about standard enthalpy of reaction, rather enthalpy of reaction. Now, what is other type of enthalpy of reaction? Standard enthalpy. Standard, I may or I may not repeat. Whenever you find this not sign, it represents it's a standard state condition. So I may say standard, I may not, I may skip the word standard, but if this not is written, that means calculations are done at standard state. Now, so this standard enthalpy of formation, as the name suggests, what is formation? If 1 mole of a compound is formed from its constituent elements in their standard state, then the enthalpy change of such a reaction is also termed as enthalpy of formation of that product. For example, let's say over here I am forming HCl. HCl gas is produced by whom? They have 2 constituents, hydrogen and chlorine. So you have to form 1 mole of HCl. So if 1 mole of HCl is formed, from whom? From its constituent element. What is its constituent? Hydrogen. Hydrogen exists as H2 gas. Other is chlorine. Chlorine exists as Cl2 gas, and in order to form 1 mole, I will use stoichiometry half and half. So how much mole of HCl is formed? 1 mole. Sir, can we write enthalpy of reaction for such a reaction? Yes, but this enthalpy of reaction, you can directly call this enthalpy of reaction as enthalpy of formation of HCl. This is the definition which you should know. Sir, so if it is another example here, HI is formed. From their constituents, yes sir. In their reference state, this is gas, this is solid, perfect sir. But how many moles are produced? 2. So for every reaction, whatever enthalpy changes, generally it is enthalpy of reaction. But I am giving you some other names for enthalpy of reaction. So this enthalpy of reaction, let's say it is x kilojoule. And I am asking you, can you tell me enthalpy of formation? Sir, but this is not, this is 2 moles are forming. You said 1 mole should form. So if for 2 moles value is x, for 2 moles value is x, so for 1 mole it will be x by 2. So what will be enthalpy of formation? Sir, it will be nothing but x by 2. It will be nothing but, sir, why not writing properly? Because after knowing enthalpy of formation, a very important thing you should always remember, which is its application. Now, you can use, see, I've told you, na, why we started defining different types of enthalpy? Sir, because enthalpy change is equal to enthalpy of products minus reactants. But this absolute value is difficult to determine. So instead of their enthalpies, what you can take is, this is the application of enthalpy of formation. Enthalpy of formation is a change, and change can be easily determined. So statistical experiments show that these all are statistical formulas. Shows that the application of enthalpy of reaction is, if you need to calculate enthalpy of any reaction, it is always equal to a summation of enthalpy of formation of product minus summation of enthalpy of formation of reactants. And because this enthalpy of formation is a change, therefore can be easily determined. But again, look at the stoichiometry. Enthalpy of formation of C into small c, D into small d. So this is product minus A into small a, B into small b. Now, this is the general I've written, a very important formula. Please remember this. We will be getting too many questions based on this. Now, other application is to, this is just basic. I've told you, let's say carbon has 2 allotropes, graphite and diamond. What is the reference state? Sir, graphite. So for graphite, statistically, experimentally, if you go and check thermodynamically, for graphite, enthalpy of formation of carbon will be 0. For diamond, it will be some value. So because for graphite it is 0, so we will know through thermodynamics, okay, graphite is the more stable forms, and hence in order to compare stability of allotropes, we calculate their enthalpy of formation. Now, again, sir, if we know this formula, now I am again going over here. Now I know enthalpy of any reaction. I do not know it is formation or not. Enthalpy of any reaction, it is given as x kilojoule. Apply that formula. Okay, sir. Now I'm using a pen because now I'm applying what result we had. So I am applying the same formula, which is enthalpy of any reaction is equal to summation of enthalpy of formation of product, which is HI. So summation enthalpy of formation of HI into 2 minus product. Sir, enthalpy of formation of hydrogen plus enthalpy of formation of I2. Sir, why you are not writing? Again, whenever elements are present in their most stable state, reference state, then you need not do any job to make them, because their formation is by the mother nature. So for all substances in their standard state, their standard enthalpy of formation is considered to be 0, because mother nature makes them. We do not have to put in any energy. So their standard enthalpy of formation is assigned as 0. So sir, if we know this also, then coming back to this, okay sir, this is standard state, so it will be 0. This is standard state, so it will also be 0. So minus 0. So what formula I have applied? Enthalpy of a reaction is equal to enthalpy of formation of product into stoichiometry minus enthalpy of formation of reactants, because it is standard state, so 0. Now you can see directly what if question is asking you enthalpy of formation of HI, then it will be what? So this is given to be x. So it will be x. Enthalpy of formation will be x by 2. Although for this simple reaction, we have done it by unitary method also. Like for 2, it is x. So for 1, it will be x by 2. Because we know the theory that formation is only defined when in the reaction, the product that is formed is 1 mole. Is theoretical definition of enthalpy of formation. Now, after knowing this The first type of enthalpy of reaction, let us also also know an energy conservation law, just given a different name. In thermodynamics, we were calling energy conservation as first law, FLOT. Over here, I'm calling it as Hess Law. Now, what is Hess Law? Common sense. What is common sense? Let's say carbon reacts with oxygen and forming CO. Let's say for this reaction, enthalpy changes delta H1. If this CO further reacts with oxygen and forms CO2, this is balanced reaction. Because delta H is extensive, so you have to be specific, balance the reaction. This is delta H1. This is delta H2. And suppose I'm taking, in the third experiment, I'm taking carbon solid and directly supplying it some more oxygen and directly forming CO2. So let's say this enthalpy changes delta H3. So I am starting from this point and I am reaching at the same point. So if I'm starting from A and reaching at same point B, you choose any path because enthalpy is also a state function. So you choose any path. The summation of energy will be, energy cannot be created nor can be destroyed. So this path was, what was the enthalpy summation? So delta H1 plus delta H2. So you either you follow this path or this path because you are reaching the same end. So enthalpies will be same. So 1 plus 2 will be equal to 3. This is nothing but Hess law, a very common sense of application of energy conservation and the property of enthalpy, that is, it is state function. Do not depend upon the path how you are making. I just depend on the states. So this 1 plus 2 equals 3. So the such questions are okay. Questions now we are practicing questions now. The question says this reaction has delta H of this. Let's say I'm saying this is delta H1. This reaction has delta H given, so the delta H stands C naught, and if delta H given, that is enthalpy of reaction only. So delta H1 given, delta H2 given. Enthalpy of change you have to calculate for this reaction. So let's say this is reaction 3 and its enthalpy is delta H3. Now, again, sir, enthalpy is a extensive quantity. So if you multiply any reaction by 2, delta H will be multiplied by 2. If you add two reactions, delta H will of the resultant reaction will also be added because it is extensive properties are additive. If you multiply by 3, it will be multiplied by 3. If you add, then the resultant will also be added. For example, you need to get this equation. How can you get this reaction from the above two reactions? Sir, carbon solid is here. Do we have carbon solid? Yes, we have carbon solid in equation 2. But how many carbon solid we have? Sir, 1. But how many you need? Sir, 3. So what do? Equation 2, you multiplied by 3. So this is equation 2, I am multiplying by 3. By looking at what? That I need 3 carbon. Now I need Fe2O3. Where is Fe2O3? Sir, in equation 1. Where is Fe2O3? Sir, in product side. Where do you need Fe2O3? Sir, in reactant side. How many you need? Sir, its stoichiometry is also 1. Its stoichiometry is also 1. So I just need it in that side. So equation 2 I multiplied by 3 and now I am subtracting equation 1. And what times of equation 1? Only 1 times. Why? Because this is also 1, this is also 1. Now what you do in your rough copy, you take equation 2, multiply by 3 and you subtract equation 1 and you write the reaction. You will definitely be getting this reaction and common things will be cancelled out. Just check. So sir, if this is the mathematical operation you are doing and obtaining this reaction for which you have calculated, you have assumed delta H and enthalpy change to be delta H3 and delta H is an extensive quantity. So delta H3 will be equal to this. So what you have done with the reaction, do with the value of delta H also. So delta H3 will be equal to, second equation value is minus 110. So minus 110 into 3 minus first value is minus 822 into 1. Do the math. So this becomes 822 and this is 330 subtracted because this is positive. So answer will be positive. So this is 2, 12, 3 is 9 and 7, 3 is 7, 3 is 4. This is 492 with a positive sign. Now, I have just done one question for you. This is nothing but proving the Hess law also. and along with that proving that enthalpy change is an extensive quantity, and hence whatever mathematical operation you do with the reaction will be done with the value of delta H also. Moving ahead. And you will get so many. I have just taken few examples. You will get so many questions. Moving ahead. Now, again, this is reaction number 1, reaction P, reaction Q, delta H1, delta H2 given. You have to form this reaction. Now, this is the same type of question. I guess this is a homework for you. I've given an answer also. This is A. So, this will be your answer. Moving ahead, similar type of question. Now, other type of enthalpy of reaction, sir. Enthalpy of phase transformations. Sir, right now we were dealing with chemical reaction. A physical reaction can also take place, and physical reaction may also involve heat exchange. So they will also be coming under the scope of thermodynamics. Yes. What is sublimation, sir? Sir, any solid into liquid. Sir, why? Okay, you can write this arrow also, but why I am writing this? Because in equilibrium, I have told you, phase transformation takes place at a fixed temperature. Temperature never changes till all of the solid has changes to liquid. So it is always a dynamic equilibrium and exists at a constant temperature. Let's say this temperature will be the freezing point, and this is fusion. So whatever enthalpy change will be happening will be known as enthalpy of fusion of ice, H2O solid. If we are writing reaction like this, then we know solid, in order to convert to liquid, we have to supply energy. So this delta H value will be positive. Let's say some x kilojoule per mole. I am not interested in the value. I am just defining that this is, although a physical change, but the enthalpy of reaction, it is enthalpy of reaction also. But this enthalpy of reaction, I am giving another name, and the name I am giving is enthalpy of fusion. And how much, because it is an extensive quantity, so if we are defining, so I will always use for 1 mole. So similarly, vaporization, sir, liquid to gas, H2O liquid to H2O gas, enthalpy change will be enthalpy of vaporization. Sublimation, solid to gas, like I2 solid changing to I2 gas. The enthalpy change of this reaction involving 1 mole will also be termed as enthalpy of sublimation of this iodine. You will get number of questions. I am just giving all the basics to you. Now, what is another type of enthalpy of combustion? As the name suggests, you take 1 mole of any compound, and what does combustion mean? Reaction with oxygen. So I am taking 1 mole of graphite, reacting with oxygen, forming the corresponding product in their reference state. Products are formed in their standard state at that particular temperature. So this you should remember also, that what carbon reacts with oxygen forms CO2. So this is a reference state of carbon when it undergoes combustion. Sir, so this is a reaction, balanced reaction. So we can write enthalpy of reaction. Enthalpy of reaction, sir, we already know. It is equal to summation of enthalpy of formation of product minus reactant. So what is summation of enthalpy of formation of products? Sir, CO2 minus reactant, sir, carbon and graphite. Sir, carbon is in reference state, so you can mark it as 0. Sir, oxygen is in reference state, you can mark that also as 0. So sir, over here 0 will come. Then why you have written? Just to make you see that enthalpy of reaction, which can also be termed as enthalpy of combustion, because I am combusting, I am burning 1 mole of graphite. So how I am defining enthalpy of combustion? If you burn 1 mole of any compound, then whatever enthalpy of reaction you get can also be termed as enthalpy of combustion of that particular substance. In this case, it is carbon graphite. So this enthalpy of reaction can also be termed as enthalpy of combustion. But enthalpy of reaction can also be written as enthalpy of formation of product minus reactant, and if reactants are in their standard state, then this value is 0. So why I have written that, sir, you should have written 0, because I want you to observe this, because this is also an observational science, that enthalpy of combustion is nothing but enthalpy of formation of CO2. So enthalpy of combustion of graphite is nothing but it is equal to enthalpy of formation of CO2. So such results can only be attained by some experimental observational truth, because I'll be defining an observational truth more. So I'm just making you understand this. That's this formula we know, this definition we derived, and through this definition and this formula, we are seeing that enthalpy of combustion of a compound called graphite is actually equal to enthalpy of formation of CO2. Moving ahead. Now, another reaction I have written, sir, this is methanamine undergoing combustion, forming CO2 because carbon reference state is CO2. Hydrogen reference state is H2O. Nitrogen reference state is N2. Nitrogen is the most stable diatomic molecule. At normal temperature, it never reacts with oxygen. So nitrogen exists as N2 gas. Now, this is what I meant by whenever you undergo combustion, you form compound in their reference state, and reference states you should know. So whenever combustion is subjected, carbon turns to CO2, hydrogen turns to water, but nitrogen turns to N2, not its oxides, because nitrogen is the most, this is an inorganic knowledge you should know. Okay. So again, the enthalpy of reaction can be written, and because this compound, how much mole of this compound is getting combusted? 1. So I can even say this is enthalpy of combustion of this methylamine. I can even say this is enthalpy of combustion of methylamine. Now, what is this? Enthalpy of formation of product minus reactant formation of CO2 plus 5/2 water. So why not written nitrogen? Now I am using this because it is reference state, so it will be 0 minus enthalpy of formation of reactant. This is methanamine and this is oxygen. Not written because it is also its reference state. Moving ahead. Now, a question comes, it is just the same question. At least you give it a try and let us check. Yes, so moving ahead, guys. I guess you can simply see that for 17 gram of ammonia, the value at this temperature and this pressure, the value of delta H enthalpy change is given. So it is just talking about the extensive property of delta H. That is, it depends upon the amount. Sir, 17 gram of ammonia has how many moles? Sir, 1 mole. So because molecular mass of ammonia is 17. So number of moles is 17 upon 17. So for 1 mole, the value is this. So the question is saying for 85 gram, it will be how much? Sir, just calculate number of moles. So 85 upon 17 is how much? I guess 5. So for 1 mole, it is this. Then for 5 mole, it will be, sir, 5 times of this value. Answer I have already written. Simple. So just look at the beauty of what the question are asked. Again, the same question. Same question. So you just have to know the basics. Now, how it is same, sir? Enthalpy of vaporization of CCl4 is given. How much? Enthalpy of what is vaporization? Sir, delta H from liquid to gas. Okay, sir. Delta H is given. Now, the question is asking you heat required for vaporization of 284 gram. Sir, we have to calculate number of moles in 284 gram. How to calculate number of moles? Sir, given weight upon molecular mass, add atomic masses. So this will, let's say, chlorine 35.5 into 4 plus 12 will give you the molar mass. So the molar mass, let's say it is M. You just do the math. So for 1 mole, the value is 30.5. So for n moles, it will be, sir, n into the value of delta H. This will give you the answer. Option is already written. Answer I've already written. Into divide you have to do. So this is just talking about the extensive nature of delta H. Now, again, the question may appear, the question is very huge. You just read the question. The question says that an athlete takes up 100 gram. Okay, sir, 100 gram of glucose athlete is having, equivalent to 1800 kilojoule of energy. So with that glucose, the athlete gains this much, 1800 kilojoule of energy. 50% of energy is gained, is utilized by athlete. Okay, so the athlete must be exercising and utilizing 50% of the energy. What is 50% of 1800? 900 kilojoule. In order to avoid storage of energy, okay, 900 athlete has utilized while doing athletics. So 900 must be there in his stomach. So the question is saying in order to avoid storage of energy, if energy stored, it will become fat. The weight of extra water he would need to perspire in gram, as in in order to now compensate for that 900 gram extra, the athlete has to lose it. How will the athlete lose the extra energy? By working out. While working out, he'll perspire. What does perspiration require? Sir, water. So the question is asking you that the athlete has to lose 50% of 1800 kilojoule. That means 900 kilojoule of energy the athlete has to lose. So we know the value of energy that has to be lost is this much joule. Now, question says, assume that there is no other, okay, he is not consuming food from anywhere else, no consumption, consuming stored energy. He'll not store any energy, he'll waste every energy by sweating it out. The enthalpy of vaporization of water is given. Okay. So if he had 1 mole of water and perspires 1 mole of water, how much energy that he'll be losing? 45 kilojoule. Because enthalpy of vaporization. What does vaporization mean? I am taking H2O liquid, dig, but I am running, exercising extra to sweat out the extra energy. So this H2O liquid will be becoming H2O gas. So this 1 mole sweat, if you remove water liquid in form of sweat, so how much energy you will be using for that? For 1 mole, you will be using 45 kilojoule. Okay, so let us make it kilojoule only because it is given kilojoule. So in order to lose 1 kilojoule of energy, how much mole of water I have to take? 1 upon 45. How much energy I have to lose? The 900 kilojoule. So how much water I have to take? Into 900. This much mole of water you should take. Sir, but question is asking in gram. So how much water I'll be taking? Sir, 900 upon 45 is the number of moles. Number of moles is equal to weight upon atomic mass, which is 18. Just do the math. I guess this is quite easy. This is 20. So 18 into 20 is 360. See, just the extensive nature of delta H the question is asking you. Now, the other question, enthalpy of formation of CCl4, water, CO2, HCl is given. Let's say I'm marking it as, because for the case of simplicity, this is A, this is B, this is C, and this is D. The magnitude of enthalpy. Sir, the question is asking enthalpy of reaction. So how do you write enthalpy of reaction, my friends? Sir, enthalpy of reaction is equal to enthalpy of formation of products. What is products? Sir, CO2. How many CO2? Sir, 1 mole. What is enthalpy of CO2? The 1, 2, 3. Okay, I write over here. I've written A, B, C, D. Value you substitute. Into divide is for you. CO2 is C plus. What is HCl? D. So this is 4D. This is of product minus. What about reactant? CCl4. CCl4 I've taken value of, I'm not taking that value. So A will be minus 105. And 2 times of water. Water is B. So plus 2 times of water. Just do the math. A, B, C, D. From there, put over here because actually the coefficient, the stoichiometric coefficient, they'll also matter. Why we have written every time? It is an extensive property. So that coefficient will also impact that how much enthalpy of formation of that particular product will also be. That particular molecule will also be accounted because delta H is an extensive property. So just the basic formula. So this is of product, this is of reactant. You put the value. That's why I've again given you the answer. So these all are your practice questions. Moving ahead. Now, solid fuel in rocket. Okay, there is some fuel. Fuel does what? Fuel gives energy. So there must be some reaction taking place. Okay, the question is telling you reaction between this and this is happening, Fe2O3 and aluminium, but they are in the ratio 1:2. Okay, that means, sir, you are taking Fe2O3 1 mole plus aluminium 2 mole because question is saying it is taken in ratio 1:2 and they will react. They will react to form. The question is also giving you enthalpy of formation. So indirectly, the question is not written the reaction, but it is hinting you that aluminium oxide is formed. So this reacts with this metal displacement Aluminium forms its oxide, formula is Al2O3. Plus iron will be just the redox thing. So here aluminium is oxidized and iron is reduced. I guess in order to balance the reaction, aluminium is balanced, oxygen, okay. In order to balance Fe, I have to write 2. That's it. Balanced. So how do you write a delta H for a reaction? So delta H we write as enthalpy of formation of product. I guess for Al2O3 it is given. Let's say I'm marking it as A and to this I'm marking as B. You do the math. So for Al2O3 value is A. Put that value with sign. So A is minus 1700, but I'm just giving you the basic of product. So this will be A plus. Sir, this is pure solid. So for pure solids, for metals in their most stable state, native state, it will be 0. So this is of product minus. What about reactant? So for this, it will also be 0. So Fe2O3, Fe2O3, it is given. Let's say value is B. This is of reactant. So you know these values, you will find delta H. But question is not asking you delta H. Again, the question is playing with mole concept. How? The question is asking you the heat evolved in kg per gram of the mixture. Sir, here, what is the mixture that we have taken right now? This is the mixture. This is the mixture which is releasing this much of energy. You will calculate this much of energy. What is the mass of this mixture? Sir, you have to calculate mass then. So what is mass of this mixture Fe2O3? Molecular mass. Fe mass is given. So 56 into 2 plus 16 into 3. This will give you, let's say this mass is M1. Aluminium is 27, but the mixture has 1 mole of this and 2 mole of this. So 2 mole of this weigh how much? So 2 into 27. That means this is 54. So M1 plus 54. So that means M1 plus 54 gram is giving you how much of heat? Delta H. This delta H is what? A minus B. You can put the value of A and B with sign. So this much heat is given by this many gram. So 1 gram will give how much of heat? So delta H upon this value. So what math you have to do? Now you know, just calculate. So 1 gram will release this much kilojoule of energy because this data is also in kilojoule. That's it. Answer I've already given. It is an integer type question. Into divide is for you because we have to save time. Moving ahead. Now, again, now. Combustion reactions are hugely asked by JEE. You can very well apply the definitions which I have told you. What definitions? Like for hydrogen, heat of combustion of, how do you write combustion reaction of hydrogen? Sir, 1 mole of hydrogen has to react with oxygen. And what it produces? H2O in order to balance this, because I need 1 mole of this. So you can write this for hydrogen also, for carbon also, and for ethanol also. The combustion is given. And question is asking you enthalpy of formation of C2H5OH. So I am first giving you a observational math without even deriving it. You can very well derive it. So sir, what is the observational math? There is an application. Like enthalpy of reaction is equal to enthalpy of formation of product minus reactant. In the similar fashion, this is very important, you should make note of this. Enthalpy of a reaction can also be calculated for any reaction. If enthalpy of combustion of reaction mixture is given in the question, then you can also calculate enthalpy of reaction. But how? Enthalpy of combustion of reactants minus product. Please keep this thing in mind. This is a very important observation. Although you can, without doing anything, you can just write whatever enthalpy of combustion we have studied like this. You can take these 3 reactions and you can form the reactions. What will be the reaction for enthalpy of formation of ethanol? Sir, formation as in 1 mole has to be formed from what? From constituent elements. What are the constituent elements of ethanol? Sir, carbon. So it will be carbon solid plus oxygen, so O2 gas, because constituent element has to be taken in their most stable state. Oxygen most stable state is this, and hydrogen most stable state is this. And how much ethanol you need to form? Sir, because enthalpy of formation is asked, so I need 1 mole. So just balance accordingly. So it will be 2 Oxygen I need 1, so it will be half. Hydrogen I need 6, so it will be 3. You can very well write these 3 reactions, apply Hess law, use those 3 equations to get this. Let's say this reaction has a value of enthalpy change delta H, like we have done in the previous question. So we will mathematically play with the 3 equations and get that. It will take time. So in order to save time, what you can do, I'm giving you this observational math, that whenever enthalpy of combustion of reaction mixture is known, you can directly calculate what? You can directly calculate the enthalpy of reaction. How? Enthalpy of combustion of reactants minus product. Remember this. It is not product minus reactant, it is reactant minus product. So you can directly get the answer. For example, I'll do this for you. So I have to calculate enthalpy of, this is the reaction. This is the reaction. Because 1 mole is getting formed, so this will be enthalpy of formation only. But I can say this enthalpy of formation is also enthalpy of reaction. So enthalpy of reaction is equal to enthalpy of combustion of reactants minus products. So what is enthalpy of combustion of reactants? Let's say for hydrogen, I am taking this value as A. For carbon, I am taking as B. For this methanol, I am taking as C. So what will be for reactants? Carbon is I have taken B. So 2B plus. What is for oxygen? Sir, oxygen never, how oxygen combines with oxygen? So for oxygen, enthalpy of combustion is always 0. Plus for hydrogen, I have taken A. How many times hydrogen? 3. So 3A. What I am taking? Enthalpy of combustion of reactants minus. What about, who is the product? Ethanol is the product. Is its enthalpy of combustion given? Yes, sir. Value I have taken as C. Put that value with sign. Into divide is on you. So 2B plus 3A minus C, you will get your answer. And please, please, please make note of this observation, because this is number of times asked by JEE. See, again the same question. Enthalpy of combustion of benzene is given and acetylene is given. And you have to calculate enthalpy change of this reaction. So this reaction will be, enthalpy change for this reaction will be of reactant, so 3 into of acetylene. Let's say this value for benzene, I'm taking value as A. For acetylene, I'm taking as B. So how much ethylene? 3B minus reactant minus product. So whatever 3B minus A value will have will be your answer. You have options also. So the same formula, I'll show you more question. This was 2022 question. Now this is 2020 question, similar question. Enthalpy of formation of ethane, you have to calculate if enthalpy of combustion of ethane, hydrogen and graphite is given. So how do you write the reaction? Sir, I have to form ethane. Ethane is what? C2H6. How it is formed? From its constituent in the most stable state. So carbon solid and hydrogen gas. This carbon solid is graphite only. This is ethane. So enthalpy of combustion of all 3 are given. Just balance them. So this is 2 and this is 3. Enthalpy of combustion of reactants minus product, but with the stoichiometric coefficient. So you just have to write the reaction as per the definition. Moving ahead. So see, similar questions are asked. Now, moving to another enthalpy. This is also very easy. This is enthalpy of atomization. What is enthalpy of atomization? Now, definition says you have to take a gaseous molecule, because if it is solid and liquid, then solid will first convert into gas. If it is liquid, then liquid will first convert to gas. First physical change will happen. Ultimately, from gas, if you heat something, after becoming gas, the bond starts getting to break. So we have defined how to define enthalpy of atomization. You just take a gaseous molecule and start breaking all its bond and form the constituent gaseous atom. So if one mole molecule is given heat and broken down into its constituent gaseous atom, so for this reaction, whatever the enthalpy change will be, it will be now termed as enthalpy of atomization. Now atomization, we know this value. But what is, sir, bond enthalpy? What is bond enthalpy? Bond enthalpy is the enthalpy change. Actually, it is energy required only because these processes are obviously endothermic. So in order to break this particular bond, what is the energy that you have to put in? That enthalpy change will be bond enthalpy. but it is the average value. Average value as in, see, I have CH4. How many C bond H CH4 has? 4. So let us break this one C bond H. So one H gone, 3 bonds are remaining. Let's say in this step, the bond dissociation required is, let's say, a kilojoule per mole. I do not know the value. The question may give you. In order to break the second bond, how much? Let's say B amount of kilojoule energy is used to break the second C bond H. For the third one, let's say this delta H, this is 1, this is 2, this is 3. Delta H 3 is, let's say it is C. Then for the last one, so the bond dissociation for last step is, let's say D. So sir, if I'm adding the 4 reactions and getting atomization, so what will be atomization? Nothing but A plus B plus C plus D. Do the math. You will get the value of atomization. Sir, but this is bond dissociation and this is enthalpy of atomization. What is bond enthalpy? Bond enthalpy is the average. As in, if you have to calculate bond enthalpy of C bond H bond, then what is the average, sir? Total energy required is enthalpy of atomization, which is A plus B plus C plus D upon, what is the average? 4. So after taking out its average, the average value is termed as its bond enthalpy. And the individual steps, if you have to use English, it is bond dissociation, first bond dissociation, second, third, fourth, so on. Moving ahead. Now, sir, bond enthalpy also has application, yes. But just like enthalpy of combustion, you can also calculate enthalpy of any reaction using bond enthalpies. But bond enthalpy, sum of bond enthalpies again of reactants minus products. Sir, we have to remember this, yes, because these are observational facts. So observational facts you have to learn and then apply in the particular question. Again, stoichiometry will be used, as in whatever number of bonds they have, reactants, multiply that also. We'll see in question. So, a very good question. So just attempt this question and then we will move forward. Yeah. So if you just try and read the theory, you will get to know what the question is actually telling you. It is all about types of enthalpies of reaction, theory as well. Enthalpy of atomization of Br2 liquid. Sir, atomization, you said that molecule has to be in gaseous state. But the question is saying enthalpy of atomization of Br2 liquid. Sir, how can I atomize a liquid? Remember? Actually, sir, you are saying remember, but you said gaseous molecule broke into constituent gaseous atom. That is true for a gaseous molecule. Now you just go to the English of it. What does atomization mean? Atomization mean I am directly changing you into your constituent atoms in your gaseous state. Sir, but technically we know through gaseous state. But if the question is supplying you with a value, you have to consider that value. Question is specifically saying it is in liquid state. So consider in liquid state. And atomization definition theory goes the same. So this value is given out to be X kilojoule. So X, we know this is X. Now, bond enthalpy of Br2 is why. What is bond enthalpy? You have bromine, but that bromine has to be in gaseous state only. Because bond enthalpy is just the dissociation of Br bond Br. And because Br bond Br has just 1, so the average will only be the 1. So actually this Br bond Br, so this is basically Br2 gas. And this energy is given out to be Y kilojoule, which is bond enthalpy of Br2. The question is not said liquid gas, because now the question is asking you that do you know what is definition of bond enthalpy? We know energy required to break a particular bond. Br bond Br. So this is Br2. So this also we know. So that means this value, liquid to gas, sir, this is phase transformation. Liquid to gas is known as enthalpy of vaporization. I hope you know this. Phase transformations, and we know in order to convert liquid to gas, this value, I do not know what it is. It will be some positive value. Let's say plus A. I do not know. So this is plus A, this is Y, and this is X. Y is also in kilojoule. Just check. Yes. So apply Hess law. What will Hess law tell you? Hess law tells us that this X will be equal to this plus this, as in A plus Y. Sir, but A not given, question is not asking you values also. Question is just asking you the relation between X and Y. So, sir, X is not equal to Y, X is A plus Y. So, X is greater than Y. So, X is greater than Y. Very good. And the question is not asking you into divide, but it is asking you, this is a JEE 2020 question. Now, moving ahead. Now, this is a cut to cut, whatever formula you have read. Enthalpy of a reaction can also be calculated. But here, question is again playing with English. The question is saying enthalpy of formation. Sir, enthalpy of formation, we know compound forms from its constant elements in their most stable state. But read the English. The question can give you a value, no? Give you a given condition. So it is giving. You have to form what? Ethane. What is ethane? C2H6, C bond C, then H3 and H3. It's an alkane. Okay, sir. This is C2H6. Now, it is forming by not constituent, it is forming by ethylene. What is ethylene, sir? Alkene. What is 2-carbon alkene is this. This is actually C2H2. How these are formed? We know from class 10th. Sir, hydrogen, it is saying also by addition of hydrogen. So, you are forming 1 mole of this, but in order to form 1 mole of this, you do not have to write the basic definition, which is actually how we write carbon solid plus hydrogen gas. Forming 1 mole of this will be actual definition of enthalpy of formation of this. But question is redefining English for you, that it is asking you, you tell me enthalpy of formation of ethane from this. So if question asking you, then you have to give the answer. So you have to tell the enthalpy change of this reaction. And to this enthalpy change, question is referring to as enthalpy of formation. So I need to calculate this delta H. So I need to calculate delta H of reaction. So delta H of reaction is equal to what? When bond energies or bond enthalpies are given, it is equal to bond enthalpy of reactant minus product. So let me do this value for you. So first let us calculate for reactant religiously, because stoichiometry also we have to see. Sir, how stoichiometry? How many C bond C we have? 1. So what is value of C bond C? Okay, let us C bond H is this, C bond C is this, then C double bond C is 615 and H bond H is this 435. I am just marking because it has given respectively, no? So people miss, even I miss. So this C double bond C is 615. How many C double bond C we have? Only 1, sir. Then plus. How many C bond H we have? 2 plus 2, 4. So what is value of C bond H? Sir, C bond H is this. 414. So 414 into 4. Plus H bond H. How many H bond H? 1. H bond H is last. 435. This is of reactant minus product. What I have product? Okay, product has C bond C, not double bond. C bond C is this 347. How many? 1 only. Plus C bond H, how much? 6, sir. So C bond H is where? C bond H is this 414. 414 into 6. This you do not have to calculate. You just do this 615 plus 435 minus, okay, minus I am opening, na? Minus 347. Sir, why you have not? This is also same, this is also same. So this is 4, this is 6, 414 minus 414 into plus 4 minus 6 will give you minus 2. So this is the math you have to do. Kindly do the math and get to answer. Answer I have already given, it is 125. Yes. So moving forward, another application of Hess law and defining few other enthalpies also, just for sake of questions. Although it is basic chemical bonding, the Born-Haber cycle of chemical bonding that you know, when we'll be discussing bonding, we'll be discussing that. But this is just that Born-Haber cycle of chemical bonding. If you do not know it, I'm giving basics also. For example, I have 1 mole of a solid. So solid is generally an ionic solid. So this is a cation and anion attracted to each other. It's an ionic solid. So when this ionic solid is subjected to water, sir, water is a universal solvent. Water has got huge hydration enthalpy. Water can dissolve any substance in itself. Especially ionic compounds are highly soluble. So if I dissolve this solid in excess of water, then water molecules will apply their attraction force and will break and will actually not chemically, they'll not break, they will hydrate, as in they will make this solid into aqueous ions. So when 1 mole of a solid is dissolved in excess of water and they form their constituent aqueous ions, the enthalpy change is termed as enthalpy of solution. I'm not writing the definition. I guess you understood this. Now, sir, when somebody is getting hydrated, initially some water molecules will circle around that particular molecule. Yes. So while circling around, can that molecule form and hydrate? Yes. So that means first I will take this solid and give it some hydration, and after getting hydrated, it will ultimately dissolve into its constituent gaseous ions. This is one thing I'm telling you. Now, here I'm using a term called hydration, but that hydration I'll be showing you in question also. We'll be using that concept also, like a solid before getting completely dissolved into ions, first get hydrated, and after getting heavily hydrated, it dissolves in form of its constituent gaseous ions. You keep this thing in mind. Now, another definition I'm giving you of chemical bonding. Sir, if a solid is changing into gas, the solid is changing into gas, this is also Na+, this is also Na+. When 1 mole of any solid is dissociated into its constituent gaseous ions, this is also a change, and this change is called delta H lattice, as in lattice enthalpy. Chemical bonding, we know. When 1 mole solid is broken down into its constituent gaseous ions, such enthalpy change is called delta H lattice. Obviously, we'll know this will be endothermic. Now, when 1 mole of gaseous ions are dissolved in excess solvent, when it is water, then this is called hydration enthalpy. This is called hydration enthalpy. And applying Hess law, so delta H solution is equal to delta H lattice plus delta H hydration. Are all salts soluble in water? No. Who are not soluble in water? Whose delta H lattice is larger than delta H hydration, because this hydration is generally exothermic. So energy is released, and this lattice is generally endothermic, so energy is absorbed. Which reaction will go forward? Which will feel good? Who will feel good? Where energy is released. Why? Because energy released, then I am stable. So this is like positive is like investment. So this is investment, and this is the output from the business. So which business will grow? Which business will run itself? Which will give money? Let's say it will give you 100 rupees and asking you for an investment of 10 rupees. So you will definitely invest because it is asking for 10 rupees and giving 100 rupees in return. So this is all chemical bonding basic, but still I'm telling you. Now, moving forward after getting this common sense, I'm giving you a direct question. The question says enthalpy of hydration. Okay, sir. Hydration is asked. Yes, beta. Of copper sulfate. Okay. So this is CuSO4. Anhydrous, as in it's a solid. Enthalpy of solution. That is, I am dissolving it into constituent ions in aqueous medium. Let's say this value is delta H solution. So I'm writing delta H1. Now, when this copper sulfate pentahydrate, okay, this value, this delta H is given. So we should just write the value only. No, why bother? Why making unnecessary values, variables? This is -70. Okay, sir. Kilojoule per mole. And when this CuSO4 dot 5H2 with water of crystallization also, you can become a hydrated. Remember I told you hydrated solid. So this hydrated solid, when given excess of water, it can also form its constituent ions. and this value is given as plus 12 kilojoule. Data is given, you can't do anything. This is 70, this is 12. Both are kilojoules, so I'm removing the unit. Simple. Now, heat of hydration of copper sulfate to array, sir. This is asking from copper sulfate to this. I told you in the previous slide. One hydration definition is when you have ions. The gaseous ion becoming aqueous ion is hydration. Another hydration, you can hydrate ion also. You can hydrate molecule also. Here I am hydrating molecule. So when copper sulfate is subjected to excess of water, completely dissolved. But sir, before getting that excess, it must have got few limited, and then limited would have become excess. So here 5 came, and when more than 5 came, it will get dissolved. So sir, this is your heat enthalpy of hydration from this to this. Let's say this value is delta H. Apply Hess law. So minus 70 is equal to this value plus 12. So it will be minus 82. Your answer is minus x. The question is also saying minus x. So what is x? 82. Simple. So unnecessarily, I'm not giving you definition. I'm directly applying and telling the definitions also and solving questions also to be time effective, because we already exceeded time. Now, enthalpy change for conversion of chlorine to Cl minus. Again, do this. Sir, chlorine to Cl minus. Okay, sir, half of Cl2 gas to Cl minus aqueous. Now, this is just chemical bonding basic. I am just iterating so that these enthalpies I have not written over here. So, just telling you with a question of JEE mains. Okay, what value is given? You have to tell me value of delta H. So, this I have to calculate. Given is dissociation. Okay, sir, dissociation. Sir, Cl2, but this is for 1 mole. And the question is asking for half mole. So, forget about this half. Cl2 is Cl bond Cl. When it is broken, it will form chlorine gas. But how, if 1 mole is broken, 2 chlorine will be produced. So, if half broken, 1 will be produced. For 1 mole, 240 kilojoule is required. So for half mole, half of 240, as in 120 kilojoule. Simple, see, simple, directly. Now, again, what is given? Electron. Eg is electron gain. Sir, gaseous ion gain electrons and form an ion. This enthalpy change is called electron gain enthalpy, and generally electron gain enthalpy is also exothermic. So it is given also. It is minus 350. So this is minus 350, this is plus 120. Now, what else? Hydration, we already know this. Gaseous ion going into aqueous ion is the hydration enthalpy. This is also exothermic. So value is also given minus 380. Now you do the math. Hess law. This equal to this plus this plus this. With sign you take, you will get your answer. Moving ahead. Answers I have mentioned over here. Now, moving ahead, again giving you one more enthalpy. Sir, we know strong acids completely dissociate and give H plus. Equilibrium we have already done ionic. Strong bases completely dissociate and form OH minus ion. H plus and OH minus ion love each other. How do we know this? Because water is not an ordinary electrolyte. That means H plus ion are in love with OH minus ion, and they directly attract each other and form water. Sir, if they both want to do this, they must be getting stable. Yes. If they are getting stable, energy is getting released. Why? Because if they are stable, its energies decrease. The energy cannot be destroyed. So where energy is gone, it has been released. And this released energy, because H plus comes from an acid, OH minus ion comes from a base, and it got neutralized. So this enthalpy change is also called enthalpy of neutralization. So whoever be the acid will give H plus. Whoever be the base will give OH minus ion. So when 1 mole of H plus reacts with 1 mole of OH minus ion, will form 1 mole of water. So the enthalpy of neutralization, which I am writing as like this, will always be a constant value. And the value you have to remember also, it is minus 57 kilojoule per mole or minus 13.7 kilocalorie per mole. Both are same, but a very important and very important data. You should remember this. So the question is also asking you this theory only, that assertion says strong acid and strong base reacts, they release itta. Yes, this is true. So this assertion is true. And enthalpy of neutralization is amount of energy liberated, because this energy will be released, hence minus. Liberated when 1 mole of H plus furnished by acid combined with exactly what is the definition is given. So both are true and explanation also is right. So this is option B. I'm giving you theory also and giving you that. Why I'm giving theory? Because these theory has been asked. Now, one thing we know from ionic equilibrium also. Sir, if I'm a strong acid or I'm a strong base, I will completely dissociate. Let's say if a strong counterpart meets a weak counterpart. We know this through ionic equilibrium. Strong counterpart would completely form H plus and OH minus ion. Let's say I have a strong acid and base is weak. But because acid is strong, so base will be forced, according to Le-Chatelier's principle, it will be forced to dissociate completely. But that forcing will require some energy. So if both were freely giving H plus and OH minus ion, energy released is this much. But if some counterpart is weak, so some amount of released energy, as in I am feeling very happy. So I have, when you are happy, when you go for a marriage, you udao paisa, you do tish and dance. So whenever molecules are feeling happy, they are giving energy. How many? How much? 13.7 kilocalorie. Yeah, minus 57.3 kilojoule. But sir, if somebody is not dissociating, I have to invest some money into them. So that value will become, in that case, and the energy enthalpy of neutralization will be less, because some amount will be invested for the weak counterpart. So why telling this? Just this theory of common sense of ionic equilibrium applied. Question is saying I am reacting HCl and NaOH. Sir, both are strong. Water is formed, energy released is 57.3. Sir, we already know this. But the question is saying if I have a strong base, we know this is a strong base, it will completely dissociate. And it's a weak acid. So weak acid will not dissociate by itself, but because base is present, so it will force the weak acid and it has to get ionized. But that forcing will be requiring some, I have to, how much money I was releasing? 57.3. So out of that 57.3, some amount I have to give to this acetic acid so that it can dissociate. So in this case, amount of energy released will be less. It will be minus, but magnitude will be less than 57.3. So what is the magnitude? 55.3. How much less? Exact differences of the magnitude. Do not see sign. Sign means energy is released. So 2 rupees. This minus this is 2 rupees. So where 2 rupees has gone? This acid must have taken that 2 rupees to ionize. And the question is only asking you, the ionization energy of acetic acid is 2. Not even have to move the pen. Moving ahead. Now, sir, first law dealt with heat and work quantification. That if I have T in this room, then heat will flow from hot T to cold place. Now, second law tells us that why reverse is not happening. Suppose I have a hot T over here and I have kept that T in this room. Why heat is not getting into, why it is not becoming more hotter? Actually, thermodynamics second law deals with spontaneity. And I'm giving you this word with a sentence, just one sentence, one line, it is finished. All the processes will be taking place by themselves. If they are taking place by themselves, they are called spontaneous process. If you open a tap in your terrace, water will flow down by itself. But reverse, if you have to supply water from the ground floor till your terrace, you have to use a motor. A motor has to be used, energy, and forcefully water has to be supplied to your terrace from the ground floor. So it is a non-spontaneous process. So spontaneity, thermodynamics can tell by using an operator, and the mathematical thermodynamic operator is entropy. So first of all, again, when a process can become spontaneous, the overall cases for any process to be spontaneous, delta S total or delta S of universe should be positive. As in, by doing that process, what is delta S total? Delta S system plus delta S surrounding, because thermodynamically we know what is universe, system plus surrounding. So whoever process can take place by themselves, which will increase the entropy of the universe. A final thumb rule, and this is the actually second law of thermodynamics, that if you want to be a spontaneous process, then while you are going in this nature, total entropy of the universe, I am not talking of your entropy, I'm not talking of system, I'm not talking of surrounding, I'm talking of value of system plus surrounding, it has to be positive. Point number one. Now, sir, what is S? A thermodynamic function. Every thermodynamic function, what value we are interested in? Change. Absolute value we are not. So change of entropy, total entropy should be positive, first thing. Now, sir, what is this entropy? Entropy is a thermodynamic function that measures the randomness present in a system. Randomness as in the degree of freedom that you have. Sir, degree of freedom as in your ability to move like anything. Now, sir, in order to just understand entropy, let's say you have a solid, you have a liquid, and you have a gas. You tell me in which state of matter degree of motion, degree of randomness will be larger? Sir, gas. The entropy of gas is higher, followed by liquid, and solid has minimum entropy. That means as temperature is increasing, absolute value of entropy is increasing. Note this. As temperature increasing, I am not talking of entropy change. I am talking of the absolute value. I am not calculating it as of now, because absolute value is difficult to quantify. But as temperature increases, degree of randomness as an absolute value of S increases. Point number one. I mean, the after one of entropy. Now, can you tell me, sir, this is gas, this is gas. If this is a solid converting to gas, entropy increasing. But if it is a gas, it is a gas, is it a gas? Go to equilibrium. Sir, 1 mole of gas producing 2 mole of gas. So delta Ng is positive. So here also entropy is getting increase. So delta S will be positive. But here delta S of system. I'm not talking of total. What is condition of spontaneity? Total entropy. But here I just know this about this. Sir, how will we relate? We'll do it later. But as of now, understand what I'm telling you. Now, adsorption of gases. Let's say this is a solid. Gases getting adsorption as in they are accumulating at the surface of the any substance. Let's say it's a solid. And gases are adsorbing as in accumulating on the surface. So gas was freely moving, now getting adsorbed. So their randomness, their motion will decrease. Yes, so entropy will decrease. So delta S will be negative. But delta S of what? Of this system. I'm not talking of total. Entropy, the increase or decrease you got. Sir, why telling this? Question. You tell me, the question is asking you, during the following process, you have to tell me in which case entropy decreased. Let us check. What is freezing of water? H2O liquid? Sir, liquid to solid, entropy, solid na? So entropy will decrease. So yes, entropy decreasing. So one is right. Okay. We have to check, so, and then answer is there. So one is right. One entropy is decreasing. So this is an option for us. Again, sir, liquid to solid, whatever temperature it is, entropy will decrease because solid is going to from liquid state. I am going to solid state. So this is also entropy will fall. Sir, 4 mole of gas forming 2 mole of gas. Entropy decreasing. Mole, although it is gas also, it is gas also. Then decide. Moles will decide. There are 4 people. They are becoming 2 people. Initially 4 were roaming around. Ha-hoo machaing. Initially 4 were roaming around, not 2 are. So entropy decreasing. This is also our answer. That adsorption we have seen, entropy decreases. Dissolution, okay. Dissolution is solid becoming aqueous. Entropy increases. So no. So what is your answer? 1, 2, 3, 4. Just check. Moving ahead. Yeah. So let's move to give a mathematical model to entropy. Sir, we already know it's an extensive quantity and a state function or thermodynamic variables are. So now, in the initial slides, we see as temperature increases, degree of randomness because motion of constituent molecules increase, so entropy increase. But very important, although S and delta S both are functions of temperature, that is also main question. Just this thing, but the delta S with temperature is inversely proportional. Let us understand this now. Let us suppose I have a system at lesser temperature and again a system at higher temperature. If I supply same amount of heat to both the system, it is experimentally observed that whatever entropy change has taken place in first system, this magnitude, this change of delta S1 was found to be greater than that of delta S2. Sir, how come this is true? See, just put a logic behind it, because it's at first place it's an experimental fact, so that's why we have came to this conclusion. But we can easily understand this also. Suppose 5 degrees Celsius as in a person having a system having lesser temperature, as in a person having not eaten for like 30 days. For 30 days, if you have not ate anything, okay, sir. If small amount of one roti, Q is same. If one roti is given to me, the amount of energy I will have with that roti, I will be tremendously happy. So my entropy, my degree of motion will drastically increase, drastically change. So delta S for such a system which is at lower temperature is higher. And if I have just eaten double burst pizza, cheese burst, double burst pizza, sir, then if somebody will give me that one roti, I will maybe I will not even eat that roti. Just for the sake of being modest, I'll say, oh, very nice, I'll take that roti, I'll not eat it, I'll keep it and utilize it. So my entropy, my randomness has not changed. Even I've kept that roti, so it has changed to a very slight extent. Similarly with entropy change, must keep this thing in mind. Now, sir, mathematically also, if you want to derive entropy, then what thermodynamic scientists did was, they have taken a system, this is the system, and surrounding is providing heat to the system. But I wish to provide heat to this system so slowly, sir. What is a very, very, very slow process which can only exist in pen and paper? Because when you draw a curve, you want to draw that curve for every x you need value of y. So you want to draw a continuous curve. But sir, practically doing process this slow is not possible. But as of now, we are deriving mathematically. So we have to be mathematically correct with this. Now, how mathematically entropy is defined, that you have to, it is a definition, so you should know this. I am giving heat to the system. Who is giving? Surrounding is giving heat to this system. Okay, sir. Let's say I am giving small amount of heat. So small amount of heat can be represented as dq. But this small amount of heat I am giving so slowly that, let's say, temperature of the system is T. I do not want the system to increase its temperature by even a little bit. I want this temperature to be constant. Sir, how can I do that? Give heat so slowly that that heat is directly converted into work. Temperature of the system will not change. So this heat is given so slowly, hence the term reversible. And because the system will work, so some randomness, system will move. So move as in randomness will change. So how entropy is defined? The change, because small amount of heat is supplied, so small change, ds. It is equal to the small amount of heat that you supplied very slowly, so reversibly, so that the Kelvin temperature of the system will remain constant. This is the mathematical definition, so you have to learn it. Now, sir, now we know mathematically, this is ds, this is dq, integrate. So let's say initially entropy was S1. Finally, it became S2. So what is integration of dx x? So dss upper limit wale S2 minus S1. So S2 minus S1 can be written as delta S. Now this is delta S of this system only. It is equal to. Now, sir, integrate this also. Sir, temperature we have to keep constant. Yes. Whatever you heat supply, temperature should not increase. So, sir, that means we have to supply heat so slowly that heat given and directly system will do randomness. And in doing that randomness, it is utilized that heat, so temperature will not rise. So, practically it is possible? No. Practically irreversible work takes place. I will just give heat. But I will give you that logic also. But let us first define it. Sir, initially what heat we have given? Nothing. Finally, what we have given? Q, but given very slowly, so writing reversibly over there in the subscript. So 1 upon T will come out constant. What is integration of dx? X. So dq, Q, upper limit is Q reversible. Remember, there is no delta Q for us. So this is Q given reversibly upon the constant temperature T. This is your beautiful formula for entropy change of a system, and see, it is inversely proportional to temperature, but this temperature is in Kelvin and it is kept constant. Now, sir, but we cannot supply heat that slowly. Do not worry. Let's say I'm at state 1. We are reaching state 2. Okay, I wish to do very slowly. You do it cut. You do it irreversibly. But mathematically, I am doing it reversibly. Does it even matter? Because S2 minus S1 as in delta S. It is a state function. The change is indifferent of the path followed. So if you are doing practically we are doing this only. But because we are calculating change, so when we find this result experimentally, it came out to be same. Very important, but a very thoughtful conclusion. Now, what will be its units? Sir, Joule per Kelvin. Moving ahead now. Sir, after deriving entropy, can you please again tell us SLOT, second law of thermodynamics? Yes. What SLOT is used for? In order to say that whether the process is spontaneous or not. Why? When process becomes spontaneous? When total entropy increases. What is total entropy of system and surrounding? Mind you, from now onwards, if I'm not writing anything in the subscript, that means I'm talking of system. And if it is total or surrounding, I will definitely write. So what I'll be doing from now, system, I will not write anything in the subscript. That means I'm talking of system. But if I'm talking of surrounding or total, I will write total and surrounding. This NCERT also follows. So for spontaneous process, what is the condition? Entropy of the universe, that is total entropy, should increase. But it is only valid for irreversible processes. Because practically reversible process. So what about reversible? Reversible forward and backward. If it is a reversible process, delta S will be 0. So delta S 0 as in, delta S is, I'm just changing this. Delta S is 0 as in equilibrium. So for reversible, you will be in a state of equilibrium because delta S will be 0. Because delta S total, I'm talking of delta S total over here. So writing total. And if delta S total is coming out to be negative, that means process is non-spontaneous, a single point agenda. And this is all experimental facts which we are learning and explaining. Let us use it. Sir, how question comes? In order to do question, first let us, we know only. Phase transformations, very much asked in mains. What are phase transformation? Solid to liquid, liquid to gas, solid to gas, sublimation, vaporization, fusion. Let's say over here I have taken fusion. So solid converting into liquid, yes. At what temperature it converts? Sir, melting point. T, solid converted. So this is T, melting point. This is the system. Okay, sir. How can you write delta S of the system? I'm not writing. Okay, for over here I'm writing. From now onwards I'll not write. So delta S system will be equal to, sir, Q upon the constant temperature T, which is the melting point. Sir, what is Q? Heat exchange between system and surrounding at if I'm giving heat to this solid, I must be giving it under atmospheric pressure, pressure constant. So heat supplied at constant pressure becomes QP, and QP through thermodynamics, you know, it is equal to delta H. So this is nothing but delta H fusion upon the constant temperature at which it is happening. If it is vaporization, so delta H vaporization upon boiling point. If it is sublimation, then delta H sublimation upon the constant sublimation temperature will be given in the question. Although vaporization and fusion are mostly famous. Now, moving ahead. Sir, we know the calculation of entropy for phase transformations. But sir, one thing. Sir, we know when solid convert, delta H will be positive. So delta S of system is positive, sir. But we know solid. For example, I have kept water, ice. This is ice, sir. Ice melts by itself automatically. How can you prove this? If it is happening and it is irreversible, solid ice will convert to liquid water. How? It will take heat from outside, from surrounding. The system will take heat. Sir, how can you prove total entropy is increasing? I'm doing that for you. Can you tell me delta system I've calculated? Can you tell me what is delta surrounding for it? Yes, sir. What is delta surrounding? Sir, if you are taking delta H fusion heat, so who is giving you that heat? Surrounding. So if you are taking as plus Q, so surrounding is giving, so heat exchange for surrounding will be minus of this Q, which is delta H. So minus of delta H fusion, because what you are gaining, I am giving. So if heat is released, I'm system, I'm surrounding, and heat is coming out from me. So if coming out, so it is minus. Because this is gaining, so it will be plus for the system. Now, but sir, obviously, if surrounding is giving heat to the system, temperature of surrounding must be higher. So the constant temperature of surrounding will be temperature of surrounding, which we know because heat is traveling from surrounding to system. So we know temperature of surrounding will definitely be greater than temperature of the melting point system. Now, can you tell me what is delta S total? The total is system plus surrounding. So what is delta S system? Delta H fusion upon temperature melting point plus what is delta S surrounding? Sir, minus delta H fusion upon temperature of surrounding. Sir, mathematics we know. Numerator is same, will come out. Sir, but this temperature is higher, so denominator is higher. So this minus value will be lower. This ratio will be lesser in magnitude, and temperature melting point ratio will be higher in magnitude. Sir, that means delta S total will come out to be positive. That's why it is spontaneous. What is spontaneous? Melting of ice. So this is how, but in mains, this is all theory I'm telling you, because theory also mains love. Advanced starts loving it. So mains also use this theory in asking ABCD questions. But what type of question you account this? Delta H vaporization given, delta S given. You have to calculate temperature. Array sir, delta S is equal to delta H upon the constant temperature T. You have to calculate. Delta S is given in joule, delta H is given in kilojoule. So 30 in joule, it is 30 into 10 is power 3. Solve the answer. I've given you answer also. Piece of cake. 24 question. Same question. This much of heat is required to melt. Okay, this is delta H then. Sodium chloride. Okay, the entropy change is found to be this is delta S. And melting point of sodium. Again, you have to calculate the same temperature melting point. Do the same formula and just try to come up with an answer. Answer I've already given 1017. Calculate. So as you can clearly observe that for irreversible case, we have done that how delta S total is always positive, greater than 0 for a spontaneous process. Sir, but for reversible process, I told you it is 0. Delta S total is 0. Let us see for some theoretical questions. For a reversible process may be isothermal, may be adiabatic. Adiabatic is very easy. Adiabatic as in Q is 0. Sir, if Q is 0, numerator is 0. So if numerator is 0, neither system is getting any heat nor surrounding is giving any heat. So delta S system, delta S surrounding, and obviously because both of them are 0, so delta S total will also be 0 for the reversible process. And what about irreversible? What about reversible isothermal, sir? When temperature is constant, so let's say this is my system, and if I am supplying, if surrounding is supplying Q amount of heat, okay, reversibly. But isothermal, so its temperature is also T and surrounding temperature is also T. So what can you say about delta S system? Sir, Q heat is given to the system, so plus Q upon given at constant temperature T. What can you say about delta S surrounding in irreversible? In the question which we have taken, the phase transformation, the temperature was different because it was irreversible. But because it is reversible, it is getting heat, so surrounding is giving heat, so it is minus Q for surrounding, but this temperature will be this T only. So if you add them up, delta S total will still come out to be 0. Now, entropy change is such a topic which clearly distinguish between mains and advance. In advance, there is whole set of, for an ideal gas, putting so much conditions on ideal gas, you can calculate entropy change for a lot of cases. But mains do not love this topic, although for all those who are much interested, I am giving you the set of formulas. These are calculation of entropy change for ideal gases for various specific cases. System also, surrounding also, total also, the sign also. But you do not have to bother about this because mains is not at all interested in it. So let us move ahead to the more important and probably the last topic of thermodynamics. Yes, so before moving on, let's just discuss this one question. Because I said that entropy. So this is a question exactly related to this formulas of yours. So let us just for once, although it is very easy to derive also. How will you derive? Sir, for entropy, you define that ds equals to what? dq upon t. For Q, apply first law of thermodynamics, then apply what is first law of thermodynamics? du is equal to dq plus dw. So replace that dq by du and dw. Du you can write as ncv dt. Then you will get a chance to integrate. Not a very big case, but I'm just simplifying that what is the general formula for an ideal, for a system whose entropy has to be calculated. Sir, general formula we can see. NCV ln T2 upon T1 plus NR ln V2 by V1. If pressure is constant, then the CV becomes NCP ln T2 upon T1. So various cases can be applied, and this one question was asked, that therefore I am again discussing it in January 2019 JEE. Now the question says there are two blocks of metal having same mass. Okay, mass is same, at different temperature T1 and T2, and brought in contact with each other and allowed to attain thermal equilibrium. So that means equilibrium must have been reached, yes, but at constant pressure. So if pressure is constant, what formula you will use? Pressure constant, so we will use NCP ln T2 by T1. What is T2, sir? Final temperature. What is T1? Initial temperature. So my formula, this is the state which I am given with. There are two blocks, temperature must be different. Let's say one will definitely be higher and second will be lower. So let us say T1 is higher than T2. I mean, obviously whoever is higher, heat transfer will take place and they will attain a thermal equilibrium. Let's say their initial temperatures are given to be T1 and T2. Let's say they reach a final temperature. What will be the final temperature? When the heat will stop flowing, when the temperature becomes equal. What will be the equal temperature? Sir, one will be higher, one will be smaller, the average. At average, that is T1 plus T2 by 2, a final temperature when reached to this level will stop the heat flow. At that point of time, you just have to calculate entropy. So what will be the total entropy? Total entropy as in of this system will be equal to entropy change. In finding absolute value is very difficult. So we are finding change of entropy change in block A plus entropy change in block B. And how to find this entropy change? For block A, you will write formula number of moles in it into Cp, because pressure is constant, into NCP ln T final upon T initial. When we say T2 by T1, it is final upon initial. So what final temperature? Let's say TF. What initial temperature? For block A, its initial temperature was T1. So this is entropy change in A block. What will be the entropy change in B block, sir? NCP, because both mass and material are same. So heat capacities, moles, everything will be same. Into ln of T final, sir. Both of them must have reached to the same temperature. But what was B block's initial temperature? Sir, T2. This is given in question. So this is the formula you got. Okay, sir. So this is the total which is asked in the question. So what is this total value? Sir, NCP will come out, yes, into this is ln of A plus ln of B. What is formula of ln of A into B? Ln of A plus ln of B. So this is ln of A plus ln of B. So recollecting, it's ln of A, which is TF upon T1, into B, which is TF upon T2. So TF squared and T2. Just put this formula, TF, we know it is NCP ln of, what is TF? Square of T1 plus T2 upon 2 square is 4. So this will be 4 T1, T2. Simple. Let us compare T1 square. Yes. So option A will be your answer. Here moles they must have taken 1. So how do we know none option has number of moles? So number of moles they must have taken as 1. Moving ahead. So now the most and the what questions are asked from thermochemistry, and then mostly questions are asked from this Gibbs free energy. Sir, why we need Gibbs free energy change? As of now, for any process is spontaneous or not, how will you know? Sir, we will calculate total entropy of the universe. If total entropy increases, then process is definitely spontaneous. If I am running a very large industry, and practically what scientists thought is, I just have to calculate whether my system will be spontaneously working or not. Why should I will work on the surrounding as well? Because in order to find entropy total, you have to calculate entropy of system also and entropy of surrounding also. So we needed an operator for the system which can whole soul tell that whether system is spontaneous or not. Because individually, neither entropy change can tell you, the entropy change of system cannot tell you about entropy change of universe can tell you about spontaneity. And enthalpy change, because through chemical bonding we know when I will proceed in forward direction, when I will get stable, I'll feel good. If I become a reactant, suppose becomes product. Why they become product? Because they must be liking into being changed into a product. If reactant is getting stable to form a product, that means product energy must be reduced. If product energy is reduced, then where energy has gone, energy must be released. So generally, initially it was thought whenever delta H is negative, process will be spontaneous. But we know when you melt ice, it is endothermic but still spontaneous. So individually delta H also cannot account, individually delta S also cannot account. So we have defined, thermodynamics have defined an operator for us, which is Gibbs free energy. And like all thermodynamic functions, it is also absolute value is difficult to determine. So what we instead determine the change. It is also extensive and a state function, and it is basically defined to check the spontaneity of a process. Now, after defining this, I do not have to look into the total universe. I will just design and look into the system. Sir, how will I do that? Let us understand its definition mathematically. So mathematically, your Gibbs free energy is defined as enthalpy minus temperature times of entropy. This is a mathematical definition, which obviously you should learn. So what will be the change? Differential change you can also calculate, and average change will be delta H equals delta H minus delta times of Ts. But this is a very, very, very important condition I am putting. At constant pressure and temperature, because what work and experiments we do on a system generally under atmospheric pressure, or maybe generally what experiments are done are under constant temperature and at constant temperature and constant pressure. So sir, That means this G you are right now defining, so this delta G is at constant temperature and pressure. Although I'll not be writing this TP all the time, I'm just telling you. So it will be equal to delta H minus, if temperature constant, it will come out. So T delta S, this is your formula in which you will definitely be landing up with a question. So this is a whole of, sir, but how can you relate whether process is spontaneous or not? So coming to the condition of spontaneity. For spontaneity, as of now, what you know? For spontaneity, we know delta S total must be positive. But why we are bothered? We do not wish to calculate entropy change for surrounding also. If we are only interested in system, so let us focus our attention on system. So this is the condition of spontaneity we had, thermodynamics had at that point of time. So putting into some mathematical tadka into it. So let us put that mathematical spice. What is delta S total? Delta S total is nothing but delta S system I am interested in plus delta S surrounding. Oh, I am not interested in, because I need to know about the system. Do you know what is definition of delta S? Yes, sir. Delta S system will be equal to Q reversible upon T. How you have taken the process at constant pressure, so that Q will be equal to QP. QP is equal to delta H of system. So if process is happening reversibly, delta H system, whatever system is getting, who is losing it? Surrounding. So I am replacing this surrounding. How? Delta S system I am not disturbing, because I want this. If I do not want surrounding, so if system has gained delta H or lost delta H, surrounding must be doing the same amount in opposite sign. So delta S surrounding can be written as minus delta H system in place of Q upon the constant temperature at which it is happening. It should be greater than 0. Now see, there are only systems, and initially also I told you, whenever I will be writing my formula for system, now I will remove this subscript because it is unnecessarily written while writing it so many times. It is a difficult job to do. Even NCERT says that if you're talking about system, do not write it in subscript. But if you're talking of surrounding or total, then write it in the subscript. So from next line, I'm removing it. Now, so if removing this T will come over here, and this minus also I'm taking to be common. So this becomes delta H minus T delta S. System I have removed. Now, this has to be greater than 0. Sir, if this has to be greater than 0, then this is all negative. So this value have to be negative, because if this is minus and this minus will become greater than 0. That means this value has to be negative. And what is this? This is what we have defined delta G as. So in place of this, I'm writing delta G of system. So minus of delta G of system must be 0, is ultimately the derivative, the derivation of delta S total equal to 0, greater than 0, which is the condition of spontaneity. So now we have a condition for system. So for any process to be spontaneous, now you do not worry about the surrounding, just calculate its delta G, and this delta G has to be negative. So if delta G is negative, process is spontaneous. If this delta G is 0, process is at equilibrium, and if it is greater than 0, it is non-spontaneous. Similarly, if everything will be taken in standard conditions, so this delta G will become delta G naught. Moving ahead. Now, sir, but this delta G has temperature also? Yes. And temperature, sir, we can change? Yes. So do temperature change have some effect on spontaneity? Definitely yes. What, sir? If you're talking of temperature, let us divide the reactions in two halves, because some reactions are exothermic, some are endothermic. For exothermic reactions, sir, delta H is negative. Okay. For endothermic reactions, sir, it is positive. Sir, why written two times? Because delta S will depend on the process. Delta entropy may, for the process, entropy may increase also, entropy may decrease also for the reaction. So delta S can be either positive or negative. Delta S can be either positive or negative, hence taking both the cases. Now, we have to just judge the sign of delta G. Now, let's say if delta H is negative. So this value is negative. So this one is negative. And if delta S is positive, then temperature can never become negative. Kelvin temperature is 0 Kelvin. That means, sir, if it is negative and it is positive, the overall answer will always come out to be a negative value, irrespective of whatever the temperature is. And if delta G is coming out to be negative, then this means process is spontaneous always, not depending upon temperature. So for such cases, process is always spontaneous. Moving ahead. If delta H is negative, if this is minus, but if this is minus, so minus minus will become plus. So this becomes a positive thing and this becomes a negative thing. If you want delta G to be negative, you have to make the magnitude of delta H higher. But what operator you have in your hand? Temperature. So just keep temperature low. So at low temperature, you will get delta G to be negative. And in this case, process will be spontaneous at low temperature. And if, sir, I increase the temperature, delta G will turn positive. So if delta G will turn positive, process will become non-spontaneous. Sir, I'm not writing it because I'm focused on being spontaneous as of now. Now, moving ahead. Let's say endothermic. If delta H is positive, this value is always positive. If delta H is positive, sir, okay, first take this thing then. If delta H is positive, yes, sir. If delta H is negative, leave the magnitude. If this is minus, minus minus becomes plus. So delta G becomes positive all the time. So such processes are always non-spontaneous. You do whatever with the temperature, they will always be non-spontaneous, and this case will always be spontaneous. Temperature has no effect in this case also and this case also. Here temperature will play a part. Here, if temperature is kept low, process will be spontaneous. And what about it? So delta H positive, okay. If delta S is positive, now T will come into effect because this is positive and this is negative. And if you want delta G to be negative, so increase its magnitude. How to increase its magnitude? Increase temperature. So at high temperature, you may attain a negative value of delta G. That means process becomes spontaneous at high temperature. So, sir, there will be a temperature when, we can calculate that temperature. Yes, and a question was asked also. Acha, let us calculate this temperature first, then I'll go to that slide. So how temperature at which delta G is 0? We know this. Acha, this equation I am skipping. Acha, let us discuss first also. In equilibrium chapter, make it fast because I need to wrap it up because you need to do questions. Gibbs Helmholtz equation relating equilibrium constant K. Go to chemical equilibrium. Although I use the same slide which I've written in the time of equilibrium. So just check that video of chemical equilibrium. Although if you just need to understand thermodynamics, I'm explaining again. This is Gibbs Helmholtz equation. Again, a statistical equation saying delta G is equal to delta G naught plus RTL in Q. At equilibrium, no effective work because delta G determines useful work. And at equilibrium, no useful work takes place. So delta G becomes 0 and Q, reaction quotient becomes K. So if this is 0, Q becomes K, we get this. So delta G naught becomes minus RTL in K. Multiplier of ln is 2.303, then ln becomes log, that is base 10. This is your formula. Here R you will put as 8.314 because this is nothing but energy, work, useful work. So its unit will be joule. Sometimes for a balanced reaction, delta G of the reaction is not given. So now apply the basic of thermochemistry that we know. Change is final minus initial. So Gibbs free energy change of formation of products minus reactants into their proper stoichiometric coefficients will give you delta G naught. So sometimes this delta G naught is hidden. How you calculate it? Using the thermochemistry we just have learned. We will see question also. Now, moving ahead. Sir, so the temperature that we were discussing, we can calculate the temperature. Yes. How? Sir, at equilibrium delta G is 0. We know this. So delta G naught becomes equal to, okay, I'm sorry. So we know delta G is equal to delta G naught plus RT ln of Q. Again telling that. At equilibrium, delta G turns 0 and delta G naught becomes minus RT ln of K. So if I want to calculate the temperature above which the process has to be spontaneous, so let us calculate that temperature. So this ln K will be equal to delta G naught upon R of, okay, if I have to calculate temperature, if I have to calculate this temperature, so this temperature will be delta G naught upon minus R times of ln K. And what is the definition of delta G? The delta G naught standard is equal to delta H naught minus T delta S naught. These formulas you will be using n number of times. So I'm just writing them again. Now, sir, or I can say, how can you find temperature? Temperature can be written as, it will be equal to delta H naught minus delta G naught upon delta S naught. This is how you can find temperature. So temperature at which delta G naught, let's say delta G naught, I am making delta G naught to be 0. So if delta G naught turns 0, can you tell me the value of temperature? Yes, sir. It is delta H naught upon delta S naught. So this is the temperature at which delta G naught will become 0. So can you increase the temperature of a system to such an extent that its delta G naught turns 0? Yes, sir. What will be that temperature? This temperature. Because at this temperature, we are mathematically assuming delta G naught turning 0. So at this temperature, delta G naught is turning to be 0. So above this temperature, this magnitude will become higher. Because if T increases above this value, this magnitude will become higher. And when this magnitude will become higher, delta G naught will always come out to be negative. So temperature at which delta G naught is 0 is this, and above this temperature, delta G naught will always be negative. That means the process will always be spontaneous. Some questions are designed. I'm discussing everything related to questions because number of questions you will be getting in your PYQs, I have to limit using some questions. Although I'm using some of the questions. I cannot use number of questions because we have to manage time as well. Now, here in this question, you are asked the magnitude of log K. Okay, sir. Log K as an equilibrium reached. So what formula you will use? This one or this one? So log K is asked, so we'll use this one. What is the formula? Delta G naught is equal to minus 2.303 RT log of K. Why 2.303? Because ln is log base E, log is log base 10. Delta G naught not given, sir, but the reaction is given to you, this. And I told you, if delta G naught of reaction is not given, how can you calculate it? Delta G of product, which is of C6H6 benzene, given out to be this. Let's say this value is small a. This is with the minus sign. So small a minus of reactant value is this, minus 2.04, but 3 times of it. So 3b. So do the math. A minus 3b will give you value of delta G naught divided by 2.303 into R, 8.314 into temperature given. Yes, 298. But this, because this is a minus, so answer will be minus of this. So this is the value of log K. What you are asked? Magnitude. So remove this minus from your mind and report this answer. Maths is your piece of work at home. Moving ahead. Now, such questions, number of questions you get. For a certain reaction, this, temperature, this, delta H naught is given, S naught is given, you have to find equilibrium constant. What formula you will use, sir? We have to combine both the formula. What both the formula? We know delta G naught is equal to delta H naught minus T delta S naught. Delta G naught is not given, but we can write delta G naught as minus 2.303 RT log of K is equal to delta H naught minus T delta S naught. Now this is maths, they will definitely want you to apply and religiously. So what values we have? We have temperature given 400, delta H naught given, delta S naught given, temperature given, what is hidden? Log K. R we know, do the math. Math you have to do, and in JEE also you over there you will be able to do when you do here. Moving ahead. You have to match these columns. See, just theory they ask like this. Delta H for exothermic process, delta H naught is negative, easy. For spontaneous process, delta G is negative, TP as in constant temperature pressure. Easy. Delta P0, delta T0 as in isobaric and isobaric and isothermal. So 2 is 3. So this is left delta H of reaction. That we can find delta H reaction by enthalpy of formation also, enthalpy of bond energy is also bond energy or bond enthalpy, but bond enthalpy of reactant minus product. So written. So actually, moving ahead is my signing off with you. Although Kirchhoff's equation, third law of thermodynamics, the Trout law, effect of entropy change with temperature, that famous graph. But these all questions, my dear friends, are meant for advance. For mains, you are supposed to know all the things. Do not know them in depth. Although I have discussed much of the cases in depth only, because I want you to gain that confidence and just apply these logic with the PYQs of mains, and post January, if you feel, first invest time in your boards and then you will be having sufficient time for advance. But till that time, till January mains, you should only invest in PYQs and theory and questions related till point of mains. All these notes you can download from the PW app, the link to which is given in the description section. So let's meet on the next chapter. This is Gaurav Arora signing off. All the best.